Some objects in the universe are so far removed from our experience that they seem to belong more to thought experiments than to the night sky. They are the quiet, final states of once massive stars, reminders that the universe is shaped by forces of an almost unimaginable scale. To understand one of these objects, we must first consider a problem of density. Think of a city, a place like Manhattan, spread over miles, its weight measured in millions of tons of concrete and steel. Now, think of our Sun, an object so vast it accounts for more than 99.8% of the mass in our solar system. A neutron star is what happens when the laws of physics take something with the mass of that Sun and compress it into a sphere that would fit neatly within the borders of that city. Welcome to the science for deep sleep. If this kind of calm exploration into the universe helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether near an ocean, a forest, a city, or somewhere quiet in between, feel free to share where you're watching or listening from. This is not a monster or a myth, but a real, physical object. It is the collapsed core of a giant star, a remnant that can weigh more than 500,000 Earths, yet spin hundreds of times a second. It is a place where the familiar rules of matter no longer apply. This is a journey to understand that object, not from a safe distance, but by exploring what it would mean to get close enough to interact with it. The result is a quiet and absolute truth about the limits of matter and energy. This is the story of the last physical process you could ever be a part of. If this kind of calm exploration into the cosmos helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether near an ocean, a forest, a city, or somewhere quiet in between, feel free to share where you're watching or listening from. The cosmic ghost. What is a neutron star? To understand the object of our journey, we must first witness its formation. A neutron star is born from the collapse of a very large star, one that began its life with at least 8, and perhaps up to 20 or 25 times, the mass of our own Sun. For millions of years, this star exists in a delicate balance. In its core, the process of nuclear fusion generates immense outward pressure, countering the relentless inward pull of the star's own gravity. It begins by fusing hydrogen into helium. As hydrogen is depleted, the core contracts and heats, allowing for the fusion of helium into carbon. The star becomes a layered object, like a cosmic onion. Each time a fuel source is exhausted, the core finds a new, heavier element to fuse in its ongoing struggle against gravity. It moves from carbon to neon, neon to oxygen, and oxygen to silicon. Each stage of this process is shorter and more rapid than the last. A star that burns hydrogen for millions of years will burn through its final supply of silicon in less than a day. Then, it reaches an endpoint. That endpoint is iron. Unlike the elements that came before, the fusion of iron does not release energy, it consumes it. The furnace at the core of the star, the one process holding back trillions of tons of matter, suddenly goes quiet. In that moment, the balance is broken. Gravity wins. What follows is one of the most significant events in the cosmos. The star's iron core, itself more massive than our Sun, collapses inward. It falls at an astonishing velocity, reaching up to a quarter of the speed of light. An object once the size of the Earth is compressed to the size of a small country in less than a second. Under the immense pressure and temperature, the very structure of matter is undone. Atomic nuclei are forced so close together that electrons are driven into protons, merging to form neutrons. The core becomes a seething, impossibly dense sphere of pure neutron matter. This new neutron core is so dense it is almost incompressible. The collapse abruptly halts. The outer layers of the star, which were falling inward just behind the core, crash into this unyielding surface and rebound. This rebound creates a shockwave that propagates outward, tearing through the rest of the star in an event known as a supernova. The star brightens, for a few weeks becoming luminous enough to outshine its entire host galaxy. This event seeds the surrounding cosmos with heavy elements forged in the star's heart: the carbon in our bodies, the oxygen we breathe, and the iron in our blood. Left behind in the center of the expanding cloud of stellar material is the object that began it all: the tiny, dense, collapsed core. The neutron star. This is the object we seek to understand. Its properties are, without exaggeration, difficult to comprehend. The first is its scale. While it may contain the mass of 1.5 or even 2 suns, its diameter is only about 20 to 25 kilometers. It is the remnant of a star, compressed into the footprint of a city. To put its density in perspective, if one could gather a single teaspoon of neutron star material, that small volume would have a mass of approximately 1 billion tons. This is the approximate weight of Mount Everest, held in a spoon. If this hypothetical, indestructible spoon were to release its contents above the Earth, the material would not create an impact crater. It would simply fall. It would pass through the Earth's crust, mantle, and core as if they were empty space, eventually settling at the very center of our planet. This is because a neutron star is, in effect, a single, giant atomic nucleus. The empty space that makes up more than 99.9% of the volume of an atom has been completely eliminated by gravity. The neutrons are packed together, forming a substance known as neutron degenerate matter. The entire star has the density of an atomic nucleus, but it is an atomic nucleus 25 kilometers wide. The physics of the impossible. To appreciate the nature of this object, we must first understand the physics that make it so formidable. Its density is just the beginning. The process of its formation imbues a neutron star with other properties that are equally extreme. The matter we are made of derives its solidity from the electromagnetic force. The electron clouds of atoms repel one another. When you touch a surface, you are feeling this repulsion. In a neutron star, gravity has overwhelmed this force, crushing electrons and protons together. So what prevents the star from collapsing further into a black hole? The answer comes from a quantum mechanical rule called the Pauli exclusion principle. In simple terms, this principle states that no two neutrons can occupy the same quantum state at the same time. The neutrons are packed so tightly they resist further compression, creating an outward force known as neutron degeneracy pressure. This pressure is the only thing supporting the star against its own gravity. If too much mass were added to the star, pushing it beyond a limit of around 2.17 solar masses, gravity would overcome this final barrier, and the star would collapse into a black hole. Next is its rotation. Think of an ice skater. When she pulls her arms inward, her spin accelerates. This is due to the conservation of angular momentum. The original giant star was rotating, perhaps slowly. When its massive core collapsed from the size of a planet to the size of a city, that rotational energy was conserved and concentrated. The result is an object that spins at an incredible rate. Many neutron stars rotate hundreds of times per second. The fastest known, a pulsar designated PSRJ 17482446 AD, spins 716 times every second. This means a point on its equator is moving at a substantial fraction of the speed of light. It is an object more massive than the Sun, spinning faster than a kitchen blender. This rapid rotation, combined with the star's origins, creates another extreme property: magnetism. The original star had a magnetic field. As the core collapsed, the field lines became concentrated, amplifying the magnetic field to a strength that is almost beyond comprehension. A typical neutron star's magnetic field is trillions of times stronger than Earth's. The most powerful magnets created in human laboratories are 1,000,000 times weaker than this. This spinning, super-strong magnetic field generates powerful beams of radiation that sweep across the cosmos like a lighthouse. If Earth lies in the path of one of these beams, We observe a regular pulse of energy, and we classify the object as a pulsar. Finally, there is the heat and radiation. A newly formed neutron star has a core temperature in the trillions of degrees. Even after billions of years, its surface remains around 1,000,000 degrees Celsius. It does not glow with the gentle, visible light of our sun, but blazes primarily in high-energy X-rays. To be near it would be to stand before a cosmic-scale X-ray source, bathed in a constant, powerful stream of radiation that would ionize and destroy organic matter instantly. Density, rotation, magnetism, and radiation. These are the four defining properties of a neutron star. A journey to the surface. Let us begin a hypothetical journey. We start from a distance of a few million kilometers. From here, the neutron star is just a point of light, visually indistinguishable from any other distant star. Yet instruments would tell a different story. They would register a gravitational field completely out of proportion to the object's apparent size. Looking at the field of stars behind it, one would notice a subtle distortion. The light from distant stars passing near the neutron star is bent, a phenomenon known as gravitational lensing. The immense gravity is curving space-time, and the light is following that curve. It is a quiet, beautiful effect, the first visible sign that the laws of physics here are more severe. Moving closer, to a few 100,000 kilometers, the environment changes. The star is still a point of light, but the radiation it emits is now a dominant force. Any craft would begin to heat, bombarded by a storm of X-rays. Its magnetic field would also become apparent. Compasses would spin uselessly, and any metallic objects would feel a persistent torque, attempting to align with magnetic field lines sweeping past hundreds of times a second. The next stage of the journey, to within 10,000 kilometers, crosses a critical threshold. Here, the force of gravity becomes a tangible, structural threat. The gravitational pull on the side of an object facing the star is now significantly stronger than the pull on the far side. These are tidal forces. They do not pull on an object uniformly, but stretch it. Any vessel would begin to experience structural strain, as it is pulled apart atom by atom. This process is known as spaghettification. It sounds strange, but the physics are straightforward. An object falling feet first toward the star would be stretched vertically as the gravity on its feet overpowers the gravity on its head. At the same time, it would be compressed horizontally. The object is extruded through a gravitational field. It is a process of horrifying, inescapable disassembly. Let us assume our hypothetical observer is now just a few hundred kilometers from the surface, no longer a coherent object but a thin, elongated stream of dissociated molecules. The neutron star would now fill the field of view, a perfect, impossibly smooth sphere glowing with the blue-white heat of 1,000,000 degrees. Its dizzying rotation would be perceptible. The surface would shimmer not with oceans or land, but with pure energy. This stream of matter is bathed in X-rays and gamma rays so intense that its atoms are stripped of their electrons. The magnetic field, now a dominant force, would warp the very shape of these atomic nuclei, elongating them into needle-thin spindles. Matter is not just being torn apart by gravity, its fundamental structure is being rewritten by magnetism. This is the final approach. 10 kilometers. 5. 1. The stream of matter is now falling at a significant fraction of the speed of light. And then, contact. It is not an impact in any conventional sense. There is no splash. The moment this stream of atoms touches the 1,000,000-degree surface, it is vaporized into a cloud of plasma. But even that is not the end. The immense gravity of the star seizes this plasma. The pressure overwhelms all other forces, and the electrons are crushed into the protons. The carbon, oxygen, and hydrogen that once constituted the observer are transmuted into a shower of neutrons. The matter is not destroyed. It is assimilated. It becomes an indistinguishable part of the star. Its mass is added to the whole, a negligible drop in an immense ocean. causing the star to spin an infinitesimal fraction faster. This is what it means to touch a neutron star. It is the most complete and absolute form of deconstruction imaginable. The cosmic significance. As terrifying as that journey is, neutron stars are also some of the most important objects for understanding the cosmos. They are not just points of destruction. They are laboratories where the laws of nature are tested at their absolute limits. For a long time, scientists wondered about the origin of the heaviest elements in the universe. Fusion inside stars can produce elements up to iron, but heavier materials like gold, platinum, and uranium required a different explanation. The answer, we now know, comes from the collision of neutron stars. In 2017, the LIGO and Virgo observatories detected gravitational waves from two neutron stars spiraling into each other. Telescopes around the world turned to witness the event, an explosion called a kilonova. By analyzing the light from this collision, scientists confirmed that these events are the universe's forges for the heaviest elements. The single collision that was observed is estimated to have produced an amount of gold equivalent to several times the mass of the Earth. The atoms in a gold rain were likely born in the cataclysmic merger of two city-sized, sun-mass objects. Beyond this, neutron stars are our only window into matter at such incredible densities. The state of the inner core of a neutron star remains a profound mystery. Is it simply a denser version of the neutron fluid in the outer layers? Or does the pressure become so great that even neutrons break down into their constituent quarks and gluons, forming an exotic state of matter? By precisely measuring the mass and radius of neutron stars, especially as they collide, physicists can test theories about this state of matter, a realm of physics impossible to recreate on Earth. They are also perfect laboratories for testing Albert Einstein's theory of general relativity. The first indirect evidence for gravitational waves came from observing a binary pulsar system, where the two neutron stars' orbit was decaying at exactly the rate predicted by Einstein's equations. This discovery earned a Nobel Prize and laid the groundwork for the direct detections we make today. Each neutron star we find provides a new test for our understanding of gravity in its most extreme form. So we return from our impossible journey. We have seen an object born from the collapse of a star. We have considered a density where a mountain's worth of mass fits in a spoon. We have explored a gravity that stretches spacetime itself and a magnetism that can reshape atoms. And we have witnessed a final assimilation, a process that involves not just the end of an object, but the dissolution of its matter into a more fundamental state. The neutron star is a quiet monument to the power of physical law. It is a reminder that the universe contains states of matter and energy that are far beyond our intuition. They are beautiful in their physical perfection and humbling in their power. They are the densest secret in the universe. The next time you look up at the night sky, at the peaceful arrangement of distant suns, remember what quiet remnants might be hiding in the darkness between them. Remember the city-sized objects, spinning silently in the cosmic graveyard, waiting patiently for understanding to catch up. The universe's most violent birth explained slowly. In the vast story of the universe, there are events so violent they momentarily outshine the galaxies that host them. This isn't a myth or a monster, but a real process shaped by deep time and the fundamental laws of physics. It is the death of a giant star, a final, furious event that forges one of the most extreme and bizarre objects we have ever discovered. What's left behind is a stellar ghost, a city-sized corpse from a star once 20 times bigger than our Sun. But this corpse is no ordinary remnant. It's an object so dense its very atoms have been crushed, leaving behind a state of matter so strange it forces us to reconsider what is possible. To understand this cosmic violence, to truly grasp how such an object is born, we have to go back to the beginning. We have to tell the story of a star, and how it was destined to die. The protagonist, a star doomed to die. Our story begins not with an explosion, but with a life. A brilliant, magnificent, and unimaginably powerful one. The subject of our story is a massive star, a true titan of the cosmos. Our own sun is a relatively modest star, but the one we're watching is a colossal giant, weighing at least 8, and perhaps more than 20 times its mass. If you were to place this star where our sun is, its fiery surface would extend far beyond Earth's orbit, and our planet would be vaporized in an instant. For millions of years, this stellar behemoth exists in a state of delicate, cosmic equilibrium. Deep in its heart is a furnace of incredible power, where a constant war is being waged. The relentless inward crush of the star's own gravity tries to squeeze it down into an infinitesimally small point, creating pressures and temperatures that are difficult to truly conceptualize, tens of millions of degrees. But gravity does not win. Not yet. Because at these temperatures, something incredible happens: nuclear fusion. The star's core becomes a crucible where hydrogen atoms, the most abundant element in the universe, are slammed together with such force that they fuse to become helium. This process releases a stupendous amount of energy. This energy, in the form of radiation, pushes outward from the core, a constant, powerful pressure that perfectly counteracts gravity's inward crush. The star finds its balance, a stable state where the inward pull of gravity and the outward push of fusion are locked in a celestial dance that will last for millions of years. Throughout this long, stable period, the star is a cosmic factory, continuously converting hydrogen into helium. It shines with a brilliant, blue-white light, a beacon in its galaxy. But this stability is finite. The star is burning through its fuel at an astonishing rate. And while millions of years may seem like an eternity, on a cosmic timescale, it is a fleeting moment. The star is living fast, and it will die young. The very process that gives it life is also sowing the seeds of its destruction. The inevitable decline, the beginning of the end. For millions of years, the star has been steadily fusing hydrogen. But no fuel source lasts forever. Deep within the core, the supply of hydrogen begins to run out. With less fuel for the furnace, the energy output drops, and the outward pressure that held gravity back for so long begins to weaken. Gravity, always patient, begins to gain the upper hand. The core, now mostly helium ash, starts to contract under the immense weight of the star. As it shrinks, the pressure and temperature skyrocket again until they cross a new threshold, around 100 million degrees. At this temperature, the helium ash is no longer inert. It becomes the new fuel. A new fire is lit as helium nuclei are fused together to form carbon. This renewed outward pressure once again halts the gravitational collapse, buying the star a temporary reprieve. But this new phase is different. The energy release is far more intense, causing the star to swell dramatically into a red supergiant. This reprieve, however, is brief. Where hydrogen burning lasted for millions of years, the helium burning phase might last only a few 100,000. When the helium runs out, the cycle repeats itself. The core, now rich in carbon, contracts again. The temperature climbs higher still, until it becomes hot enough to ignite the carbon. What follows is a frantic, cascading series of fusion stages. The star begins to form a complex, layered structure, much like an onion. At its center, a contracting core forges ever heavier elements, while shells around it continue to burn the fuel from previous cycles. Carbon fuses into neon. Neon fuses into oxygen. Oxygen fuses into silicon. Each of these stages is exponentially shorter and more violent than the last. Carbon burning might last for centuries. Neon burning, a single year. Oxygen burning, a few months. And in the final, desperate stage, silicon burning lasts for just one day. In its final moments, the star's core has become a factory fusing silicon into a range of elements, all the way up to iron. And here, the star's life truly comes to an end. Iron is fundamentally different. Up to this point, every fusion reaction released energy, providing the pressure needed to fight gravity. But iron is the most stable atomic nucleus. Fusing it into something heavier doesn't release energy, it consumes it. The furnace goes out. For good. An inert iron core, about the size of the Earth but containing 1.4 times the mass of our Sun, now sits at the star's center. It generates no energy. It is held up only by a quantum mechanical principle known as electron degeneracy pressure, which states that electrons resist being squeezed too closely together. But the silicon burning shell is still raging, dumping more and more iron ash onto the core. The mass grows, second by second, pushing it ever closer to its absolute limit. The battle is over. Gravity has won. The climax, the core collapse supernova. The end, when it comes, is almost incomprehensibly fast. The iron core finally crosses its critical mass. Electron degeneracy pressure, the final pillar of support, fails catastrophically. In less than a second, the core begins a cataclysmic implosion. A sphere of matter the size of Earth plummets inward at a staggering velocity, reaching up to a quarter of the speed of light. As the core collapses, the temperature soars to over 100 billion degrees. The energy is so intense that it begins to destroy the very iron nuclei the star spent its life creating, a process called photodisintegration. This absorbs even more energy, accelerating the collapse further. At the same time, the density becomes so extreme that electrons are literally crushed into protons, forming neutrons and releasing a flood of tiny particles called neutrinos. This is a pivotal moment. The removal of electrons causes the electron degeneracy pressure to vanish, and the collapse becomes a runaway freefall. But the creation of neutrinos is the real game changer. These ghostly particles barely interact with matter, and they stream out of the core carrying about 99% of the event's total energy. In just 10 seconds, the collapsing core radiates more energy via neutrinos than our Sun will in its entire 10 billion year lifetime. The core continues its terrifying plunge, shrinking from the size of the Earth to a dense ball just a few tens of kilometers across. At this point, the density is that of an atomic nucleus itself. There are no more atoms, just a hyperdense soup of tightly packed neutrons. And then, the collapse stops. It's halted by a new quantum force called neutron degeneracy pressure. The core becomes an impossibly hard, incompressible object. It doesn't just stop, it bounces. The inner part of the core overshoots its equilibrium and rebounds with tremendous force, creating a titanic shockwave that begins to blast outward. Meanwhile, the star's outer layers, oblivious to the core's collapse, are now in freefall, crashing down onto the newly formed neutron core. The shockwave slams into this infalling material and stalls, smothered by the sheer tonnage of matter raining down. But then, the neutrinos play their final, crucial role. A small fraction of them, just about 1%, get trapped behind the stalled shockwave, depositing their immense energy and reheating it with unimaginable force. This is the final push. The revitalized shockwave becomes an unstoppable blast, tearing through the star's outer layers and flinging them into space at 10% the speed of light. This is the supernova explosion. For a few brilliant weeks, the light from this single event outshines its entire host galaxy. The corpse, birth of a neutron star. The cosmic fireworks fade. The shockwave in the star's outer layers expand into a beautiful, glowing cloud known as a supernova remnant. But at the heart of the explosion, a new and extraordinary object remains. This is the neutron star. It is one of the most extreme objects in the universe, a testament to the sheer power of gravity. What's left is a sphere with a mass up to twice that of our Sun, but it has been crushed into a diameter of only about 20 kilometers, the size of a city. To speak of its density is to approach a concept our minds struggle to grasp. A single teaspoonful of neutron star matter would weigh about 10 billion tons, as much as Mount Everest. A single sugar cube-sized piece would weigh more than the entire human population combined. This incomprehensible density exists because a neutron star is essentially one gigantic atomic nucleus. The atoms that make up our world are almost entirely empty space. If an atom were the size of a football stadium, its nucleus would be a marble in the center. A neutron star is what happens when you take all that empty space and erase it. The properties of this object are as extreme as its density. The surface gravity is about 200 billion times stronger than on Earth. An object dropped from 1 meter above its surface would hit it at over 7 million kilometers per hour. And then there is its spin. As the massive core collapsed, it conserved its angular momentum, like an ice skater pulling in their arms. The core, which may have rotated once every few days, speeds up dramatically. A newborn neutron star can spin hundreds of times every second. The fastest known example rotates over 740 times every second, its equator moving at a significant fraction of the speed of light. Inside the monster, the structure of a neutron star. If we could somehow journey inside this cosmic remnant, we would enter a realm of physics so alien it sounds like fantasy. Its interior is layered not with different elements, but with different, increasingly bizarre states of matter. Beneath a thin atmosphere of superheated plasma, we find the outer crust. This layer is a solid lattice of extremely heavy, neutron-rich atomic nuclei, embedded in a sea of electrons. The material here is estimated to be tens of billions of times more rigid than steel. As we descend into the inner crust, things become truly strange. The pressure increases to such a degree that neutrons begin to drip out of the atomic nuclei, forming a frictionless superfluid. The nuclei themselves are forced into bizarre configurations. When these structures were first theorized, physicists gave them whimsical names based on their shapes. This is the realm of nuclear pasta. Near the top, the nuclei are squeezed into spherical clumps called gnocchi. Deeper, they merge into long strands of spaghetti, and then flat, lasagna, sheets. Beneath the pasta, we reach the outer core. Here, all the nuclei have dissolved completely into a uniform quantum fluid of superfluid neutrons and superconducting protons. It's this superconducting core that is believed to generate the neutron star's colossally powerful magnetic fields. Finally, we arrive at the inner core. This is the true frontier of physics, a region of such extreme density that our current theories begin to break down. We simply don't know for certain what happens here. One possibility is that the neutrons themselves dissolve into their fundamental constituents, a quark-gluon plasma, or a soup of free-roaming quarks. Recent studies suggest there is a high probability that these quark matter cores exist. The center of a neutron star is a natural laboratory for exploring the fundamental laws of nature, holding secrets that could rewrite our understanding of matter itself. This journey from a dying star to a sea of quarks pushes our understanding of the universe to its absolute limit. If you find these deep dives into the most extreme corners of the cosmos as fascinating as I do, and you want to continue exploring these mysteries, take a moment to subscribe. Your support makes it possible to explore these massive topics and bring the wonders of the universe directly to you. Now, back to the chaotic afterlife of our stellar corpse. The aftermath and cosmic echoes. A neutron star is not a silent corpse. Its birth is violent, and its afterlife is anything but peaceful. Two of its most spectacular manifestations are pulsars and magnetars. The first real understanding of these objects came not from an image, but from a faint, persistent signal. In 1967, a graduate student named Jocelyn Bell Burnell was scanning the skies with a new radio telescope when she discovered something strange. A series of perfectly regular pulses, repeating every 1.3 seconds. When the signal was first discovered, the team struggled to understand how it was supposed to exist at all. The regularity was so unnatural that they half-jokingly nicknamed the signal, LGM-1, for "little green men." But soon, Bell discovered more of these signals from other parts of the sky. This wasn't an alien civilization, it was a new type of star. They had discovered the first pulsar. We now know that pulsars are rapidly rotating neutron stars. They inherit the original star's magnetic field, but it becomes concentrated to an unbelievable degree, trillions of times stronger than Earth's. As the neutron star spins, it funnels beams of radiation out from its magnetic poles, which sweep through space like a lighthouse beam. If one of these beams happens to cross Earth, our telescopes detect a regular pulse. This was the rhythmic beat of a cosmic lighthouse that Jocelyn Bell Burnell had found, the ghost of a star that had died long ago. But there is an even more extreme incarnation, the magnetar. A magnetar's magnetic field is another 1,000 times stronger still, a quadrillion times that of Earth's. It is the strongest magnetic field known in the universe. If a magnetar were to appear halfway to the moon, it would wipe the data from every credit card on Earth. Its life is incredibly violent. The magnetic field places enormous stress on the star's crust, occasionally causing it to crack in a starquake. In December 2004, a starquake on a magnetar 50,000 light-years away unleashed a burst of gamma rays. In 0.2 of a second, it released more energy than our Sun produces in 250,000 years. The wave of radiation was so powerful it measurably disturbed our planet's ionosphere. The "so what?" cosmic significance. It's a spectacular story, but it's easy to feel disconnected from it, as if it's just a grand drama playing out in the distant universe. But the truth is, this process is not just a story about death. In a very real sense, it is a story of creation, and it's the reason we are here. The first stars in the universe were made almost exclusively of hydrogen and helium. Every other element that forms the basis of chemistry and life had to be created somewhere. That somewhere was inside the hearts of stars. As we saw, massive stars spend their lives fusing lighter elements into heavier ones: carbon, oxygen, nitrogen, all the way up to iron. But it's not enough to forge these elements, they need to be distributed. A supernova is a profoundly generous act. The explosion blasts all of those newly made elements out into the cosmos, enriching the thin gas and dust between the stars. The explosion itself is a furnace for creating even heavier elements, like gold, silver, and platinum. Every piece of gold jewelry was born in the final, violent moments of a dying star. These scattered elements then become the raw materials for the next generation. The enriched clouds of gas and dust collapse to form new stars and, crucially, new planetary systems. Our own solar system formed from one such cloud, enriched by the ashes of countless supernovae that lived and died billions of years ago. So, when you look at your own hand, the iron that allows your blood to carry oxygen was forged in the core of a massive star. The calcium in your bones, the carbon in your cells, it is all, as Carl Sagan famously said, star stuff. This is the ultimate legacy of this violent birth. The death of a massive star is not an end. It is a vital part of a grand cosmic cycle of death and rebirth. The universe destroys in order to create. Our journey has taken us from the brilliant life of a massive star, through its frantic death throes, and into the heart of an explosion that outshone a galaxy. We have witnessed the moment of collapse and the birth of the impossible object it leaves behind, the neutron star. We've explored this city-sized corpse, a place of nuclear pasta and mysteries that push the boundaries of known physics. We've seen its afterlife as a pulsar and as a cosmic monster, the magnetar. But the most profound truth is its connection to us. This violent birth is not a distant phenomenon. It is the source. The universe's most violent act of destruction is also its most profound act of creation. The very fabric of our world, and of our bodies, is woven from the ashes of these events. We are, all of us, children of the supernova. And so, as we look up at the night sky, we can see it not just as a collection of distant lights, but as a graveyard and a nursery, a place of both endings and beginnings. And it leaves us with a lingering question. What other secrets, what other fundamental truths about our universe, are locked away inside these impossible objects, quietly strange, waiting for us to understand them? Thank you for joining this deep dive into the universe's most violent birth. If you want to continue exploring the cosmos and its most fascinating phenomena, please subscribe and hit the notification bell so you don't miss our next journey. And let me know in the comments what cosmic mystery you'd like to see explained slowly next. The incredible truth of a neutron star explained slowly. In the quiet, deep expanses of space, most stars live for billions of years, their light a steady and familiar presence. They are the calm, predictable anchors of the cosmos. But some do not fade so quietly. They leave something behind. A remnant so extreme, it stretches the very idea of what matter can be. Imagine a star far more massive than our own sun, collapsing under its own weight. Collapsing and collapsing, until it is no larger than a city. What is left is not a star. It is something else entirely. It is an object where the atoms that form our reality have been taken apart and remade into a substance so dense, it has no earthly comparison. Today, we're taking a slow and steady journey to understand this remnant, the neutron star. We will quietly uncover how it forges a new kind of matter from the wreckage of the old, creating something that challenges the limits of physics and of imagination itself. If this kind of calm exploration into the cosmos helps you unwind, consider liking the video and subscribing to the channel. The life of a giant. Before we can understand the remnant, we must first understand the life that came before it. Our journey does not begin with an end, but with a life of almost unimaginable scale. Picture a star, not like our sun, but a true cosmic giant, born with at least 8, and perhaps up to 25 times, the mass of our own. These are the supergiants of the cosmos. From the moment they ignite, their lives are fast and intense. Where our sun will leisurely burn for 10 billion years, these giants consume their fuel in a frantic blaze that lasts only a few million years. Inside the core of this star, a quiet, immense tension exists. It is a balance between two of the universe's most fundamental forces. On one side, there is gravity. The star's own enormous mass is trying to pull it inward, a relentless and steady pressure. If gravity were unopposed, the star would collapse in an instant. But it is not unopposed. Pushing back against this collapse is the outward pressure from nuclear fusion. In the star's core, the heat and pressure are so extreme that hydrogen atoms are fused together to create helium. As the star ages, helium is fused into carbon, carbon into neon, and so on, moving up the periodic table. Each of these fusion reactions releases a tremendous amount of energy. This energy pushes outward, creating a thermal pressure that perfectly balances the inward pull of gravity. For millions of years, the star exists in this delicate equilibrium. It is a perfectly balanced sphere of incandescent gas, held together by its own gravity and held up by its own fire. This process of creating heavier elements is the star's lifeblood. It forges the material that will one day make up planets, asteroids, and even us. But this process has a limit. The star continues to fuse elements, creating oxygen, silicon, and sulfur, but this chain of creation comes to an abrupt and final stop at one particular element: iron. The inevitable end, the supernova. Fusing elements up to iron releases energy. Fusing iron into anything heavier, however, does not release energy, it consumes it. Iron is the final ash. It is the end of the line for a star's internal furnace. When the core of our massive star fills with this iron ash, the furnace quietly goes out. The outward pressure, which had held gravity at bay for millions of years, vanishes. The balance is broken. And gravity, the patient, constant force, finally takes over. What happens next is one of the most profound events in the known universe. With its support gone, the star's core collapses under its own immense weight. In less than a second, a region containing the mass of more than 1.5 suns implodes. The outer layers of the star, finding nothing beneath them, begin to fall inward at nearly a quarter of the speed of light. The core continues to shrink at an impossible rate, becoming hotter and denser, until something new, something incredibly powerful, finally pushes back. This sudden halt in the core's collapse is like hitting a wall at unimaginable speed. The infalling outer layers slam into this newly formed, ultra-dense object. The result is a shockwave of monumental proportions, which rebounds and tears outward through the star's collapsing layers. This shockwave, carrying with it an immense blast of particles called neutrinos, has enough energy to blow the star apart. This is a Type II supernova. For a few weeks, the exploding star can outshine its entire host galaxy, a single point of light blazing with the brilliance of 100 billion suns. The explosion scatters the elements forged over the star's lifetime across the cosmos. The carbon in our cells, the oxygen we breathe, the silicon in the rocks beneath our feet, all of it is returned to the interstellar medium, ready to form new stars and new planets. But our story does not end with the explosion. Our focus is on what was left behind. In the heart of that fading cloud of gas, buried in the center of the cataclysm, lies the remnant. The quiet heart of the giant star. The incredibly dense, city-sized object that stopped the collapse. The remnant. What is left? What remains is a neutron star. All the mass of a star larger than our Sun has been compressed into a sphere so small it defies our sense of scale. A typical neutron star is only about 20 kilometers or 12 miles in diameter. To put that in perspective, a neutron star would fit comfortably within the boundaries of a large city. Think about that for a moment. An object that was once millions of kilometers across is now compressed into a space you could drive across in under 30 minutes. Our Sun has a mass of about 333,000 Earths. A neutron star packs at least 1.4 times that much mass into a ball the size of a city. This simple fact, immense mass in a tiny volume, is the key to everything that makes a neutron star so unusual. It is the source of all its incredible properties. To truly understand this, we need to leave the scale of cities and stars, and journey deep into the fabric of matter itself. We need to talk about density. The heart of density. When we think of something dense on Earth, we might think of rock or lead. But in the grand scheme of things, these materials are almost entirely empty. All normal matter, everything you have ever touched, is made of atoms. And atoms, as we learn, are mostly empty space. Picture an atom. It has a tiny, dense nucleus at its center. Far away from that nucleus, in a vast cloud of seeming nothingness, are the electrons. If you were to scale up an atom so that its nucleus was the size of a marble, the electron cloud would extend for hundreds of meters in every direction. The space in between is vast and empty. The solidity you feel when you touch a table is not its particles touching your particles. It is the repulsion between the electron clouds of the atoms in your hand and the atoms in the table. You are feeling force fields pushing against each other in empty space. A neutron star is what happens when that empty space is removed. During the supernova, the force of gravity becomes so immense that it overcomes the force that keeps atoms apart. It takes those vast, empty atoms and squeezes them until the electron clouds collapse. The electrons are driven from their orbits and are forced inside the protons in the nucleus. The result is a substance made almost entirely of neutrons, packed together as tightly as the universe allows. The empty space is gone. We are left with a material that has the density of an atomic nucleus, but on a macroscopic, city-wide scale. This is where the analogies become difficult to hold in the mind. Imagine you could take a single teaspoon of neutron star material. That tiny volume would have a mass of over 5.5 trillion kilograms. That is roughly 900 times the mass of the Great Pyramid of Giza. A matchbox filled with this material would weigh around 3 billion tons. If we were to take our entire planet and compress it to the density of a neutron star, the Earth would shrink to a sphere just 305 meters in diameter. You could fit the entire crushed mass of our world inside a sports stadium. This is the reality of a neutron star. It is not just heavy. It is a fundamental reordering of matter. The very concept of atoms ceases to exist. There are no electron shells, no chemical bonds. There is only a sea of subatomic particles, crushed together by a force that has annihilated the void. This density gives rise to an equally incredible gravitational field, about 100 billion times stronger than Earth's. An object dropped from 1 meter above its surface would hit it in a microsecond. But how is this possible? And what stops gravity from collapsing it all the way into a black hole? The answer lies in a quiet and profound process, where the building blocks of reality are transformed. Forging neutrons, a cosmic alchemy. To understand how a neutron star gets its name, we need to return to the moment of its birth. As the star's core implodes, the density and pressure climb to levels impossible to replicate on Earth. The atomic structure of matter, stable for billions of years, finally gives way. The first resistance to this collapse is something called electron degeneracy pressure. It is a purely quantum mechanical effect. Electrons are a type of particle called a fermion, and fermions are governed by a quiet but absolute rule. No two identical fermions can occupy the same quantum state at the same time. You can think of it as a fundamental refusal to be in the same place with the same properties. The electrons resist being squeezed together, not because of their charge, but because of this quantum rule. They create a pressure that has nothing to do with heat, but everything to do with not being allowed to share the same space. For a smaller stellar remnant, like a white dwarf, this pressure is strong enough to halt the collapse. But in a massive star, the core is much heavier. There is a critical mass, the Chandrasekhar limit about 1.44 times the mass of our Sun. If the collapsing core is heavier than this, gravity is so powerful that even the quantum refusal of electrons is not enough. Gravity overwhelms electron degeneracy pressure. The squeeze becomes so intense that electrons are driven into the atomic nuclei, where they encounter protons. Under this pressure, a fundamental transformation occurs, inverse beta decay. An electron is forced to merge with a proton. Their charges cancel, and they become a single, neutral particle, a neutron. A small particle called a neutrino is also released, carrying away energy. This happens over and over throughout the collapsing core. Protons and electrons are systematically combined, their identities erased as they are fused into neutrons. The core, once made of iron, is rapidly transforming into a substance that is about 90% pure neutrons. This is the origin of the name, neutron star. It is, for all intents and purposes, a single, gigantic atomic nucleus, bound together by gravity. But this raises a question. If gravity was strong enough to overcome the pressure of electrons, why doesn't it keep going? What stops this city-sized ball of neutrons from collapsing further into a black hole? The star has a second, much more powerful quantum resistance to offer. The quantum shield, neutron degeneracy pressure. Just like electrons, neutrons are also fermions. They, too, obey the Pauli exclusion principle. They, too, refuse to be packed into the same quantum state. So, as the core collapses into a sea of neutrons, a new and far more powerful resistance arises, neutron degeneracy pressure. The principle is the same, but the effect is much stronger. Neutrons are much more massive than electrons, which allows them to be packed much more tightly before their quantum nature pushes back. As gravity tries to crush these neutrons together, another quantum effect comes into play, the Heisenberg uncertainty principle. This principle states that you cannot know both the precise position and the precise momentum of a particle at the same time. The more you confine a particle, the more uncertain its momentum becomes. In the hyper-dense core of a neutron star, neutrons are confined to an incredibly small space. Their positions are known with great precision. As a result, their momentum becomes wildly uncertain and, on average, incredibly high. The neutrons are forced to move at relativistic speeds. This frantic motion creates a tremendous outward pressure. It is this pressure, born from the fundamental rules of quantum mechanics, that finally stands up to gravity. Neutron degeneracy pressure is the final line of defense for matter against total gravitational collapse. It holds the neutron star up, preventing it from becoming a black hole. Gravity is trying to crush a city-sized object heavier than the Sun, and the quantum nature of neutrons is pushing back with just enough force to achieve a terrifying, perfect stalemate. This quantum shield is immensely powerful, but it is not infinite. There is a limit, known as the Tolman-Oppenheimer-Volkoff (TOV) limit. The exact value is still being refined by research, but it is thought to be somewhere between 2 and 3 times the mass of our Sun. If a neutron star ever exceeds this mass, nothing known to physics can stop the final collapse. The bizarre surface and interior. While we might imagine a neutron star as a simple ball of neutrons, the reality is likely far more complex. The extreme gradients of pressure and density create distinct layers, each more exotic than the last. The surface of a neutron star is nothing like the surface of a planet. It has a solid crust, but it is the strongest material in the universe. The intense gravity pulls the surface into an almost perfect sphere. Any mountains would be at most a few millimeters high before being crushed flat. Just beneath a thin atmosphere of superheated gas, we find the outer crust. Here, there is a rigid lattice of extremely heavy atomic nuclei, swimming in a sea of electrons. It is a solid crystal of unimaginable strength and density. Deeper, in the inner crust the pressure increases. It becomes so great that neutrons begin to drip out of the nuclei and exist as a free-flowing liquid, moving through the solid lattice of now neutron-deficient nuclei. And here, things get truly strange. At the base of the crust, the nuclei themselves are thought to lose their spherical shape. The immense pressure forces the matter into bizarre, complex structures, which physicists have nicknamed nuclear pasta, Depending on the density, the nuclei are thought to morph into shapes resembling spaghetti, lasagna, or gnocchi, all immersed in a sea of free neutrons. This is not just a quirky name, it is a genuine prediction of nuclear physics under extreme conditions. Beneath the pasta, we cross a threshold. The pressure becomes too great for any nuclei to exist. We enter the outer core a uniform fluid of mostly neutrons, with a smaller fraction of protons and electrons. This fluid is thought to be a superfluid, meaning it can flow with zero viscosity. Finally, we arrive at the heart of the neutron star, the inner core. What happens here is one of the biggest mysteries in physics. The pressures are so extreme that even our understanding of neutrons might break down. Some theories suggest the neutrons themselves are crushed, breaking apart into their fundamental constituents, quarks and gluons. The core could be a state of cold quark matter, something that may not exist anywhere else in the modern universe. The spinning top of the cosmos. The collapse that creates a neutron star also concentrates its rotation, due to the conservation of angular momentum. The easiest way to understand this is the spinning ice skater analogy. An ice skater spinning with her arms outstretched rotates at a certain speed. When she pulls her arms in, her rotational speed dramatically increases. Her mass is the same, but by bringing it closer to her axis of rotation, she spins faster. The same thing happens to a star. The original massive star was rotating, perhaps very slowly. When its core collapses from hundreds of thousands of kilometers down to just 20, its rotation speeds up by an astonishing amount. Newly formed neutron stars can spin hundreds of times per second. The current record holder, PSRJ 174824446 AD, rotates an incredible *** 716 times every single second. An object more massive than our Sun, the size of a city, is spinning faster than a kitchen blender. This rapid rotation, combined with another inherited property, gives rise to one of the most famous phenomena associated with neutron stars, pulsars. The original star's magnetic field is also concentrated by the collapse, amplified to strengths a trillion times that of Earth's. Crucially, this powerful magnetic field is often not aligned with the star's spin axis. This misaligned field accelerates particles near the magnetic poles, causing them to emit intense beams of radiation. As the neutron star spins, these beams sweep across the cosmos like a lighthouse. If a beam happens to sweep across Earth, our radio telescopes detect a regular pulse of energy. This is a pulsar. When they were first discovered in 1967 by Jocelyn Bell Burnell and Anthony Hewish, the regularity of these pulses was so precise they were briefly labeled LGM1 for little green men. It seemed possible they were signals from another civilization. But scientists soon realized they were seeing the clockwork rotation of these incredible cosmic objects. We aren't seeing the star flicker. We are seeing a steady beam being swept past our line of sight. The cosmic magnets, magnetars. While all neutron stars have incredibly strong magnetic fields, some are even more extreme. These are the magnetars**, the most magnetic objects known in the universe. A magnetar is a type of neutron star with a magnetic field 1,000 times stronger than a normal pulsar's. We are talking about fields of up to 100 billion Tesla. The strongest magnets made in a laboratory on Earth are only a few dozen Tesla. The magnetic field of a magnetar is so powerful it is difficult to comprehend. If a magnetar were placed halfway to the moon, it could wipe the data from every credit card on Earth. This immense magnetic field is under constant stress. The solid crust of the magnetar can be fractured by the shifting field lines, causing ***, starquakes, ***. These events release an enormous burst of energy in the form of X-rays and gamma rays. One such event, recorded in 2004 from a magnetar 50,000 light-years away, released more energy in a fraction of a second than our Sun has in the last 250,000 years. These objects are rare, representing the most extreme end of an already extreme family. We've journeyed from the life of a giant star, through its profound end, and deep into the quantum nature of its remnant. If you are finding this slow journey into the extreme fascinating, consider subscribing to the channel. It allows us to continue exploring these quiet, cosmic truths together. Now, what happens when these remnants are not alone? When worlds collide, the kilonova. Many stars are not solitary. They are born in pairs, locked in a gravitational dance. If both stars are massive enough, they can both end their lives as supernovae, leaving behind a binary system of two neutron stars, orbiting each other in a silent spiral. This dance cannot last forever. According to Einstein's theory of general relativity, these orbiting masses create ripples in spacetime itself, gravitational waves. These waves carry away orbital energy. As the system loses energy, the two stars slowly draw closer. Their orbit shrinks, and they spiral faster and faster. In the final few minutes, it becomes a runaway process. The two city-sized objects, each heavier than the Sun, are now whipping around each other thousands of times a second, screaming out gravitational waves. Then, they collide. The result is a kilonova*, an event where the two neutron stars merge and tear each other apart. A significant fraction of their neutron-rich matter is flung out into space. This is where the final piece of a cosmic puzzle falls into place. We mentioned that stars can only fuse elements up to iron. So where do heavier elements like silver, platinum, uranium, and gold come from? The answer lies in the heart of a kilonova. The ejected material is a hot, dense cloud of almost pure neutrons. In this environment, the rapid neutron capture process or our process occurs. Atomic nuclei are bombarded with so many neutrons so quickly that they grow heavier and heavier. These unstable nuclei then decay over time into the stable heavy elements we see today. On August 17, 2017, the LIGO and Virgo observatories detected the gravitational waves from two neutron stars merging. Telescopes around the world turned to the location and saw the unmistakable signature of heavy elements being created. A single neutron star merger can produce quantities of gold and platinum equivalent to several times the mass of the Earth. This was a monumental discovery. It confirmed that the gold in your jewelry, the platinum in a catalytic converter, it was very likely forged in the brief, spectacular collision of two dead stars. Every time you hold a piece of gold, you're holding a fragment of a kilonova. The final limit, the brink of oblivion. What happens after the collision? The merged object is now a single, more massive body. And this brings us back to the TOV limit. If the final mass is below this critical threshold, it will likely settle into a new, larger, rapidly spinning neutron star. But if the combined mass exceeds the limit, the story ends differently. Gravity finally overwhelms even the immense power of neutron degeneracy pressure. There is no known force that can stop the subsequent collapse. The object continues to shrink, past any form of matter we can describe, until its entire mass is concentrated into a singularity. A new black hole is born. Even a stable neutron star can gain mass over time by pulling material from a companion star. If it accretes enough matter to be pushed over the TOV limit, it will meet the same fate. After a life as one of the universe's most extreme objects, it will wink out of existence, leaving behind only the quiet darkness of an event horizon. Our slow journey has taken us to the very edge of how matter can exist. We began with a star, a familiar point of light. We witnessed its end and followed its crushed heart into a new state of being. We found a stellar remnant the size of a city but heavier than our sun, a place where gravity has unmade the atom. We discovered a quantum resistance made of neutrons, holding back the final collapse. We saw these objects spin into cosmic lighthouses and collide to forge the heaviest elements in the universe, before perhaps vanishing forever. The neutron star is a monument to the laws of physics pushed to their absolute limits. The next time you look at the night sky, remember that hidden among those peaceful, twinkling stars are these remnants. These city-sized atomic nuclei, these celestial spinning tops, these factories of gold. And remember that the very matter that makes our world precious was born from their incredible, violent, and beautiful truth. If you enjoyed this deep dive into the cosmos, please consider liking this video and subscribing for more journeys into the most fascinating corners of our universe. Let us know in the comments what other cosmic mysteries you'd like us to explore slowly. Your body vs 200 billion Gs of gravity. In the quiet emptiness of space, there are objects that stretch the idea of what matter can be. They are not stars in the familiar sense, burning with gentle fusion, but cosmic relics born from the violent collapse of stars far larger than our sun. One such object is a neutron star. It is a sphere perhaps only 20 kilometers across, yet it contains more mass than our entire sun. A single teaspoon of its material would outweigh a mountain. Its gravity is one of the most powerful forces in the known universe, around 200 billion times stronger than the pull we feel on Earth. This is a journey through the physics of that environment. It is a thought experiment to understand what happens when the fragile, complex chemistry of a human body meets a force of this magnitude. The story is not one of impact or being crushed in a conventional sense. It is a story of deconstruction, a quiet and complete dissolution into fundamental particles. It is a look at the boundary where biology and chemistry give way entirely to the raw, unforgiving laws of physics. Welcome. The approach, a deceptive calm. The journey begins in the silent vacuum between stars. From a distance, the neutron star is just another point of light, indistinguishable from the countless others. But as the distance closes, observations begin to emerge that do not fit our everyday experience. The star is small, barely the size of a city, and yet its presence feels immense. This is because a neutron star's gravity doesn't just pull on matter. It reshapes the fabric of spacetime itself. Light, the messenger of the cosmos, must follow these curved paths. One of the first signs of this is an effect known as an Einstein ring. Light from stars positioned directly behind the neutron star is bent around it, creating a shimmering halo. The neutron star is acting as a gravitational lens, distorting the universe behind it into unfamiliar shapes. Then, another unusual observation appears. As you draw closer, it becomes possible to see more than just the front of the star. Its gravitational field is so profound that it pulls light from its own far side, wrapping it around the edges toward the observer. The star appears larger than it is, a sphere whose entire surface seems, impossibly, to be visible all at once. There is no sound, no stellar wind. There is only gravity, and its influence is beginning to grow. Millions of kilometers out, a return journey is already no longer possible. The escape velocity, the speed required to break free from its pull, has surpassed what any conventional engine could achieve, exceeding 150,000 kilometers per second, half the speed of light. For comparison, leaving Earth requires a speed of just 11 kilometers per second. The journey is now a one-way path, accelerating exponentially. The space around the star is not always empty. In some systems, a neutron star is surrounded by a swirling disk of matter, the shredded remains of a companion star or other material that strayed too close. This accretion disk, as it is known, glows with intense heat, emitting vast amounts of X-rays as its material spirals inward at nearly the speed of light. For this thought experiment, however, we will imagine an isolated star, and a vessel shielded from radiation, to observe the effects of gravity alone. Just a few thousand kilometers away, the star is now a shimmering sphere. Its surface is a solid crust of iron nuclei and electrons, crushed into a crystalline lattice hotter than the core of our Sun. The gravitational pull is no longer an abstract concept, it has become a physical gradient. Even inside a protective bubble, a differential pull would become apparent. The force is measurably stronger on the parts of the body closer to the star. This is the beginning of the end. These are tidal forces. The same principle that causes the gentle rise and fall of Earth's oceans is about to be expressed with a strength that is difficult to comprehend. Here, it is the mechanism that will begin the process of disassembly, piece by piece. The zone of no return, spaghettification in the extreme. At 1,000 kilometers from the surface, the final moments of the journey begin. The acceleration is immense, reaching a significant fraction of the speed of light. The view is a vortex of distorted spacetime, but attention is now drawn to what is happening to the body itself. The tidal forces are increasing exponentially. Gravity, as we understand it, is a uniform pull. But here, the gravitational gradient is so steep that different parts of the body are subjected to vastly different forces. The part of the body closest to the star, the feet, for instance, is pulled with a force thousands of times stronger than the pull on the head. This begins as a stretching sensation. Within a fraction of a second, the body's structure begins to fail. Joints dislocate as the skeletal system is pulled beyond its limits. The vertebrae separate. This process is known as spaghettification, a name that sounds almost gentle, but describes a complete structural disintegration. At the same time, a second tidal effect is at play. As the body is stretched vertically, it is also compressed horizontally. All gravitational force is directed toward the star's single, central point. This means the sides of the body are squeezed inward, as if being forced through an impossibly small aperture. This compression accelerates the breakdown of tissues and bone. A few hundred kilometers from the surface, the body is no longer a cohesive whole. It has become an elongated stream of organic matter, accelerating downward. Consciousness would have ceased almost instantly, as the speed of biological processes cannot keep pace with the speed of this deconstruction. The process continues, moving from the macroscopic to the microscopic. Cellular membranes are torn apart, spilling their contents into the vacuum. This stream of biological material is now approaching the star at more than half the speed of light. The tidal forces have moved beyond tissues and are now acting at the molecular level. Chemical bonds, the connections that hold molecules together, are no match for this gravitational shear. The force differential across a single molecule is now great enough to break it apart. What was once a body is now a thin, glowing stream of individual atoms: carbon, oxygen, hydrogen, and the other elements of life. This atomic stream, kilometers long but only meters wide, is hurtling toward the surface. The transition from a human form to this atomic mist has taken less than a second. Even here, the process is not complete. A neutron star's gravity is so extreme that it can overcome the forces that hold atoms together. An atom is mostly empty space, with a nucleus orbited by a cloud of electrons. The tidal force is now strong enough to stretch the atom itself, stripping the electrons away from their nuclei. This is ionization. What was a stream of atoms is now a stream of plasma, a superheated soup of bare atomic nuclei and free electrons, all screaming toward the surface. There is no biology left. There is no chemistry. There is only the physics of gravity, and the surface has not yet been reached. The moment of contact, annihilation. The idea of touching a neutron star is not quite right. There is no gentle landing, no solid surface to stand on. There is only a final, cataclysmic transition. The stream of plasma that was once a body, now stretched over kilometers and moving at over 100,000 kilometers per second, finally arrives. Let us pause to consider the forces. On Earth, gravity accelerates objects at 9.8 meters per second squared. On the surface of a typical neutron star, that acceleration is approximately 2 times 10 to the 12 meters per second squared. This is the 200 billion times the force of gravity on Earth mentioned earlier. The term crushed is insufficient. The electromagnetic forces that give matter its structure and solidity are insignificant compared to this level of gravity. But this arrival is not a gentle placement, it is an impact at half the speed of light. As the particles strike the star's thin, plasma atmosphere, their immense kinetic energy is converted into other forms with near total efficiency. The impact generates a colossal burst of gamma rays and X-rays. The energy released from a mass equivalent to a human body would be staggering, a flash of light briefly outshining that tiny region of the star itself. The matter itself, the carbon nuclei, the protons, the electrons, does not stop at the surface. It is driven into the star's crystalline iron crust by pressures that exist almost nowhere else in the universe. Here, the fundamental forces of nature are all that stand against gravity's pull. The pressure becomes so great that electrons are forced to combine with protons in a process called inverse beta decay. A proton and an electron merge to become a neutron and a fleeting neutrino. The protons in the atomic nuclei are transformed. The carbon and oxygen that once formed the basis of life are crushed into a sea of pure neutron matter. The material becomes part of the star. There is another force at play here, one with its own profound effects: the magnetic field. Neutron stars possess some of the most powerful magnetic fields known to exist. Long before reaching the surface, this field would have taken hold of the charged particles, the bare nuclei and free electrons, forcing them to spiral along invisible channels toward the star's magnetic poles. This magnetic field is also strong enough to distort the shape of atoms themselves, stretching their electron clouds into long, thin spindles. In such an environment, the rules of chemistry are rewritten. The final moment, then, is a twofold event. It is an impact of unimaginable kinetic energy, and it is a gravitational magnetic crushing that forces nuclear transformation. The body's atomic identity is erased, and its matter is absorbed into the strange, degenerate material of the star. The entire event, from the first gentle pull of the tidal forces to this final absorption, would have taken only a few seconds. The physics of obliteration, a deeper look. We have told the story of this journey, but to understand it, we must look at the physics that makes a neutron star so extreme. It is a story of a battle between gravity and the forces that hold matter apart. A star like our Sun exists in a stable equilibrium. The inward pull of gravity is balanced by the outward pressure from nuclear fusion in its core. But in stars much more massive than our Sun, this process continues until the core is filled with iron. Fusing iron consumes energy rather than releasing it. When the fuel runs out, the outward pressure vanishes and gravity wins. The core collapses catastrophically in a fraction of a second. The star's outer layers are thrown off in a supernova explosion, an event that can briefly outshine its entire galaxy. What remains is the collapsed core. If the core is massive enough, it becomes a black hole. But if its mass is within a certain range, roughly 1.4 to 2 times that of our Sun, something remarkable occurs. The collapse is so intense that it overcomes the forces that keep atoms structured. Electrons are squeezed into protons, forming neutrons. An object with more mass than our Sun is compressed into a sphere just 10 to 20 kilometers in diameter. The result is matter so dense it is essentially a single, gigantic atomic nucleus made almost entirely of neutrons packed tightly together. This is called neutron degenerate matter. The only thing preventing this object from collapsing further into a black hole is a quantum mechanical principle known as neutron degeneracy pressure. Simply put, the laws of quantum physics forbid two neutrons from occupying the exact same state, creating a powerful outward pressure that holds gravity at bay. This extreme density is the source of the star's properties. By packing so much mass into such a small radius, the surface gravity becomes astronomical. This, in turn, leads to the profound curvature of spacetime described in Einstein's theory of general relativity. The tidal forces that tear matter apart are a direct consequence of this steep curvature. This warped spacetime also affects time itself. This is known as gravitational time dilation. The deeper an object is within a gravity well, the slower time passes relative to a distant observer. On the surface of a neutron star, time ticks noticeably slower. From the perspective of an object falling in, the outside universe would appear to speed up, its distant history flashing by in the final moments. Finally, there is the escape velocity. For a neutron star, it is often around half the speed of light. This makes it a cosmic point of no return. A neutron star is perilously close to being a black hole, an object where the escape velocity is exactly the speed of light. The journey was a one-way trip toward an object that is just one step shy of being a prison for light itself. The aftermath, an anonymous addition. The body is gone. Its matter is now an indistinguishable part of the neutron star. What happens to it now? The atoms that once formed cells are now a thin smear of supercompressed neutrons. Arriving with immense kinetic energy, the matter has added a minuscule amount of heat and mass to the star. The impact site, which flared with incredible energy, cools in an instant, its radiation propagating out into space. To a distant observer, it would be a completely imperceptible flicker. The mass that was contributed now becomes part of the star's structure. The surface of a neutron star is thought to be a solid crust, about a kilometer thick, made of atomic nuclei and a sea of electrons. It is trillions of times more rigid than steel. The newly formed neutrons are integrated into this system, crushed by the layers above and the gravity below. Beneath this crust, the physics becomes even more exotic. As pressure increases, neutrons are thought to arrange themselves into strange configurations, nicknamed nuclear pasta. There may be layers of spaghetti, lasagna, and gnocchi, all representing different geometric arrangements of neutron matter. Deeper still, in the core, the pressure may be so great that even neutrons break down into their constituent quarks. The core could be a sea of strange quark matter, a state of matter so extreme it may not exist anywhere else in the universe today. The particles that were once organized into a living being are now part of this quantum soup, their individual histories erased. The star itself barely registers the arrival. A typical neutron star has a mass of about 2.8 nonillion kilograms. The addition of, say, 80 kilograms of mass is an increase of less than 1 part in a 30 septillion. It is a rounding error on a cosmic scale. You have become a silent, anonymous part of a cosmic graveyard. The bigger picture, cosmic laboratories. The journey we have just taken is a brutal one. It highlights our own fragility in a universe that is often unimaginably powerful. But neutron stars are more than just cosmic hazards. They are invaluable laboratories for physics. They are the only places where we can observe matter at such incredible densities. By studying them, physicists can test the limits of our understanding of the fundamental forces. The behavior of matter in a neutron star's core tells us about the strong nuclear force in ways we can never replicate on Earth. Their powerful gravitational fields allow us to test Einstein's theory of general relativity under the most extreme conditions. The way a neutron star bends light, the way time dilates in its presence, and the way binary neutron stars emit gravitational waves have all provided stunning confirmation of his predictions. The discovery of pulsars, rapidly rotating, highly magnetized neutron stars that sweep beams of radiation across space like a lighthouse, was the first observational evidence that neutron stars existed. These celestial clocks are so precise they can be used to test fundamental physics. Furthermore, these dead stars are paradoxically responsible for creating some of the essential materials for life. While stars can create elements up to iron, heavier elements like gold, platinum, and uranium require a more energetic process. It is now believed that the collision of two neutron stars is the primary source of these heavy elements. The gold in your jewelry, the uranium in a power plant, it was likely forged in the heart of a neutron star collision, its debris scattered across the galaxy to eventually become part of our solar system. So, while a personal encounter with a neutron star is the ultimate destructive scenario, these objects are a crucial part of the cosmic story. They are the remnants of stellar death, the crucibles of the heavy elements, and the ultimate testbeds for our understanding of the universe's fundamental laws. From a safe distance, a neutron star is a marvel, a testament to the extremes the universe can produce. It is a city-sized atomic nucleus, a gravitational behemoth, and a factory for precious metals. But to approach it is to witness the boundary where physics becomes a process of complete deconstruction. The journey to its surface is a systematic unraveling of what it means to be matter. It begins with the stretching of form, proceeds to the shredding of tissues, the snapping of molecular bonds, the ionization of atoms, and culminates in the transformation of atomic nuclei. One does not hit the surface. One is unwritten by the fundamental forces of nature. The 200 billion gigaseconds of gravity is not just a number. It is a force that warps space, slows time, and crushes matter out of its very form. It is a quiet reminder that we exist in a gentle, protected corner of a universe that is, in many places, built on a scale that is difficult to imagine. It shows that what seems normal to us is only a small, surviving slice of what is possible. Surviving a neutron star is impossible, and here's why. This is a journey to a place where the familiar rules of matter break down. Where gravity, light, and magnetism are taken to their most extreme forms. It is a place no living thing could ever visit. But by imagining the journey, we can begin to understand the object waiting at its end. A celestial body so dense and so strange, it challenges our understanding of the universe itself. We are going to walk through, moment by moment, what happens when a human body meets the most violent physics in the cosmos. Let's begin. Imagine reaching out your hand across the silent vacuum of space. You see a star no larger than a city, hanging there like a small, distant jewel. But in the instant before your fingers could register its touch, you would simply cease to be. You wouldn't be burned in a familiar way. You wouldn't be crushed into a single point. You would be disassembled, systematically, by forces that operate on a level far beyond our everyday experience. The question isn't whether you would survive, that is not possible. The question is, in this meeting between human biology and cosmic extremity, what happens first? Is it the gravity, hundreds of billions of times stronger than Earth's? Is it the radiation, an invisible storm that can sterilize planets? Or is it the magnetic field, a force so powerful it can change the shape of atoms from 1,000 kilometers away? This is not a single event. It is a sequence of impossibilities. And we are going to explore each one. The cosmic remnant. What is a neutron star? Before we begin our one-way journey, we need to understand the object we're approaching. What exactly is a neutron star? The name sounds simple, but the reality is something else entirely. A neutron star is not a star in the way we think of our sun, a bright, stable ball of gas. A neutron star is a remnant. It is the hyper-dense core left behind after a massive star, somewhere between 8 and 20 times the mass of our own sun, ends its life in a supernova explosion. For millions of years, that original star was a balanced system. The outward pressure of nuclear fusion in its core fought a quiet, constant war against the inward pull of its own gravity. But all stars have a finite lifespan. Eventually, the fuel for fusion runs out. When it does, gravity wins. Instantly and completely. The star's core, which might contain 1.5 times the mass of our sun, collapses in on itself in less than a second. The outer layers of the star fall inward, crashing against the collapsed core, and then rebound in one of the most energetic events known to science, a supernova. For a time, this explosion can outshine its entire galaxy. This process forges the heavy elements that are scattered across the cosmos. The iron in our blood and the calcium in our bones were all created in a furnace like this. But at the center of the expanding cloud of dust and gas, a truly alien object is left behind. The core. During the collapse, the pressure is so great that it overcomes the forces that give atoms their structure. Electrons are forced into protons, creating neutrons. The entire core, with more mass than the Sun, is crushed into a sphere only about 20 kilometers, or 12 miles, across. Imagine the entire mass of our Sun squeezed into an area the size of a city. That is a neutron star. The density is difficult to comprehend. A single teaspoon of its material would weigh billions of tons, more than all of humanity combined. This isn't just dense matter. It's a new state of matter called neutron degenerate matter. The empty space that makes up 99.9% of everything we know has been squeezed out of existence. This collapse does two other things. First, as the star's core shrinks, its spin increases, just like an ice skater pulling in their arms. Some neutron stars spin hundreds of times every second. Second, the star's original magnetic field is compressed into that small volume, amplifying it to unimaginable levels, often a trillion times stronger than Earth's. These are the fundamental properties of the object we are approaching. A city-sized sphere of impossible density, spinning at incredible speeds, and surrounded by one of the most powerful magnetic fields in the cosmos. And we are about to get very close. The approach, an invitation to oblivion. Our journey begins at a distance that might feel safe, though the word safe is already beginning to lose its meaning. We are one astronomical unit away, the distance from the Earth to the Sun. From here, the neutron star is just a point of light. But the space around it is already behaving strangely. The first clue is a subtle distortion. The neutron star's gravity is so intense that it bends the fabric of spacetime around it, acting as a powerful gravitational lens. The light from stars and galaxies far behind it is warped into arcs and duplicate images, as if you were looking through the curved base of a glass. Because of this extreme light bending, you could see more than half of the star's surface at once, as light from its far side is wrapped around toward you. As we move closer, a new force emerges: radiation. Neutron stars are not just dense, they are incredibly hot. Surface temperatures can approach 1,000,000 degrees Celsius. They radiate this energy away primarily as X-rays and gamma rays. If the neutron star is a pulsar, one that spins rapidly and has magnetic poles that don't align with its axis of rotation, it sweeps beams of high-energy particles through space like a cosmic lighthouse. Even tens of thousands of kilometers away, this radiation would be overwhelming. It's not a gentle wind, it's a focused torrent of high-energy photons and particles. Any conventional spacecraft would fail. The radiation dose would be instantly lethal, shredding the DNA in every cell. But for this thought experiment, we will imagine we are shielded from it, so we can observe the other forces at play. We are a quiet observer, ready to witness the full sequence. We continue inward, crossing a threshold of a few thousand kilometers. The gravitational pull is now immense. You are no longer approaching the star. You are falling toward it, caught in a current from which there is no escape. It is here that the first of the truly transformative forces begins to make itself known. It is a force that will not just end a life, but physically unmake a body. It is a tidal force, and the effect it creates is known as spaghettification. The gravitational nightmare, death by spaghettification. On Earth, gravity feels uniform. The pull on your head is effectively the same as the pull on your feet. But gravity weakens with distance. Near a small object with an incredibly strong gravitational field like a neutron star, this difference in pull over the length of a human body becomes the most powerful force you encounter. This difference is a tidal force. Let's imagine you are falling feet first. At a distance of a few hundred kilometers, it would begin as a gentle stretching sensation. Uncomfortable, but not yet overwhelming. The neutron star is pulling on your feet with noticeably more force than it is pulling on your head. You are being elongated. As you fall closer, this stretching intensifies exponentially. The force is no longer gentle. It has become stronger than the material strength of the human body. Your joints would be the first to separate. Your spine would then begin to lengthen, vertebra by vertebra. Soon, the tidal force would be stronger than the tensile strength of your bones. They would fracture, not from an impact, but from being pulled apart from within. Still, the matter that was you falls, and the process accelerates. The stretching force now exceeds the strength of the molecular bonds holding your tissues together. Your skin, muscles, and organs are unraveled. It is not a clean break, but a steady drawing out. The complex organism that was a body becomes a long, thin stream of biological matter. This is spaghettification. You are being extruded through a gravitational field. And the process has another dimension. As you are stretched vertically, you are also compressed from the sides. Any part of your body not perfectly aligned with the center of the star, your shoulders, for example, is pushed inward. The stream of matter becomes thinner and thinner. Before you were even a few kilometers from the surface, you no longer exist in any recognizable sense. You are a ribbon of dissociated cells and organic molecules, thousands of meters long, but perhaps only atoms wide. Consciousness would have ended long ago, but the matter that once made up a body continues its silent, terrifying fall. This stream of atoms has been disassembled by gravity, but it is about to encounter a force that is, in some ways, even more fundamental. The magnetic hellscape, atomic disassembly. If the tidal forces were a blunt instrument, the magnetic field is something else entirely. It acts on the very building blocks of matter. A typical neutron star has a magnetic field that can be 1,000,000,000,000 times stronger than Earth's. The most powerful MRI machines create fields of around 100,000 Gauss. The field we are entering is billions of times stronger than that. And some neutron stars, known as magnetars, are stronger still, with magnetic fields up to 1,000 times more powerful. From a distance of 1,000 kilometers, a magnetar's field would be lethal on its own, not through heat or radiation, but by distorting the atoms of your body until the chemistry that supports life is no longer possible. Let's step into that field. The human body is made largely of salt water, full of moving electrical charges. The magnetic field would immediately act on these. The iron atoms in the hemoglobin of your blood, for instance, are magnetic. They would be torn from their molecular structures. Every red blood cell would be disrupted as its core component is pulled away. The stream of matter that was you is no longer just organic material. It is now a plasma, with its components forcibly aligned to the star's magnetic field lines. But the most profound violence is happening at the atomic level. In our world, atoms are roughly spherical, with electrons moving around the nucleus in cloud-like orbitals. In the grip of a quadrillion Gauss magnetic field, this structure cannot exist. The magnetic force is so powerful it overwhelms the electrical forces that define an atom's shape. The electron clouds are squashed and stretched into incredibly long, thin cylinders, hundreds of times longer than they are wide. The very idea of an atom as we know it is gone. Your constituent atoms, the carbon, the oxygen, the hydrogen, are reshaped into something alien. This is no longer chemistry, it is a high-energy physics experiment, and your matter is the subject. The bonds between these new, needle-shaped atoms would be entirely different, forming bizarre, polymer-like chains, all perfectly aligned with the magnetic field. Any resemblance to the complex organic molecules that once formed your cells is gone. The matter has been re-engineered into a new and much simpler form. So, to trace our journey so far, the body has been stretched into a plasma filament by gravity. And now that filament has had its very atoms reshaped into microscopic needles by magnetism. It has been destroyed on a biological level, and then on a chemical and atomic level. There is only one final step in this process of deconstruction: the impact. Impact, the final annihilation. The stream of distorted, ionized atoms that was once a person is now in its final descent, traveling at a significant fraction of the speed of light. It is about to strike the surface of the neutron star. This surface is not something one could stand on, even without the gravity. It is a crystalline crust of iron and other heavy elements, locked into a rigid lattice by intense pressure and magnetic fields. Despite the star's high temperature, the pressure is so great that the material is solid. This crust is also almost perfectly smooth. The star's gravity is so powerful that any mountains or other features are crushed down to a height of just millimeters. As your atomic stream strikes this crust, the energy released is immense. Your mass, accelerated to relativistic speeds, is converted into energy. The impact of what was once a single human body would release more energy than thousands of large nuclear bombs, creating a flash of gamma rays and X-rays that would be briefly visible from a great distance. But the story does not end with a flash. The matter that made you up is now driven into the crust, where the pressure becomes absolute. Here, the nuclei of your atoms, the last recognizable structures, are finally overcome. The protons and neutrons that once formed the carbon, oxygen, and hydrogen of your body are squeezed so tightly together that they lose their individual identities. They are crushed into the neutron degenerate soup of the star itself. You have not just died. You have been systematically deconstructed. Your biological form was unraveled by tidal forces. Your chemical form was rewritten by the magnetic field. Your atomic form was vaporized on impact. And now, your subatomic components have been assimilated. The neutrons that were once part of you are now an indistinguishable part of the star. Your matter has been added to its mass. Your existence is reduced to a brief flash of energy in the cosmos. In the end, to touch a neutron star is to become part of it. So, how do you survive a neutron star? The answer is simple: you don't. From the moment you enter its influence, you're subject to a sequence of forces, each more fundamental than the last. First, you are exposed to a level of radiation that would end life instantly. Then, your body is stretched and unraveled by tidal forces in a process of cosmic spaghettification. Before that process finishes, you are overtaken by a magnetic field that re-engineers your atoms into alien, needle-like shapes. Finally, the unrecognizable plasma that remains impacts the surface at nearly the speed of light, releasing enormous energy and being crushed into the indifferentiated matter of the star itself. Gravity, radiation, and magnetism, each is absolute on its own. Together, they represent a place where the familiar structure of matter cannot hold. A neutron star isn't just hostile to life, it is hostile to the physics that makes life possible. They are cosmic remnants, the quiet, city-sized tombstones of once mighty suns. And they serve as a humbling reminder. In a universe of incredible beauty and wonder, there are also corners of unimaginable physics. There are strange objects in the dark. And thankfully, they are very far away. The universe is filled with objects that defy imagination, from the gentle nebulae where stars are born to the violent remnants they leave behind. Learning about these extremes helps us appreciate just how special and fragile our own small corner of the cosmos is. If you enjoyed this journey into the impossible, consider subscribing for more quiet explorations into the most awe-inspiring phenomena in space. And let us know in the comments, what other cosmic object would you like to understand better? Every horrifying way a neutron star would end you. Somewhere in the quiet expanse of our galaxy, there are objects that stretch our understanding of matter. They are not living things. They are what remains after the spectacular death of a massive star. One such object is no bigger than a city, perhaps just 12 miles across, yet it holds the mass of 1.5 suns, compressed into a space so tight that the rules of the universe begin to change. This is a neutron star. This is a journey of thought, an exploration into what would happen if a person could get close to such an object. It is a quiet, step-by-step chronicle governed by the cold, unforgiving laws of physics. A look at how the complex structures of the human body would be deconstructed, from the first subtle distortions of space-time to the final assimilation of matter. It is a reminder that the universe experiments with physics at scales far beyond our own. If this kind of calm exploration into the cosmos helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether under a clear night sky, in a bustling city, or somewhere quiet in between, feel free to share where you're watching or listening from. The approach. A fall into a slower time. The journey begins in the deceptive stillness of deep space. Millennia ago, a star more than 8 times the mass of our Sun reached the end of its life. It collapsed, and then, in a final, brilliant event, it exploded in a supernova. The outer layers were cast out into the cosmos, seeding space with the raw materials for new worlds. But the core did not. It collapsed inward, gravity overwhelming all other forces. Protons and electrons, the building blocks of familiar matter, were crushed together until they merged, becoming a sea of neutrons. The result is a stellar corpse just 12.5 miles across, yet weighing as much as 466,000 Earths. From thousands of miles away, it is little more than a point of light. It doesn't radiate the warm glow of a star like our Sun. It is a hard, sterile light, mostly in the X-ray spectrum, invisible to the naked eye but visible to scientific instruments. For now, the gravitational pull is negligible. But with every passing second, the distance closes. The first indication of the star's true nature would not be visual but mathematical. A few thousand miles out, navigational systems would struggle to calculate a stable trajectory. The problem would not be mechanical, it would be space itself. The neutron star's gravity, over 100 billion times stronger than Earth's, warps the fabric of spacetime into a deep, inescapable well. The path forward is no longer a straight line, it is a slide down a cosmic slope. From this vantage point, the starfield itself would begin to distort. The light from stars near the edge of the neutron star would appear to bend, warped by a powerful gravitational lens. It would even be possible to see stars that are physically behind the neutron star, their light guided around its edges. The darkness of space would seem to fold in on itself. It is a quiet, mesmerizing, and deeply unfamiliar sight. Here, another subtle change would become apparent. Time itself is running differently. Due to the immense gravity, time near a neutron star flows more slowly relative to the rest of the universe. The gravitational time dilation factor is significant. For every 10 years that pass for a distant observer on Earth, only about 7 or 8 years might pass for an observer on the star's surface. The journey inward is a journey into a slower stream of time. As the distance closes to a few hundred miles, the situation becomes critical. Any vessel is no longer under power, it is a projectile. The neutron star is now a visible, terrifying disk. It does not have the roiling, gaseous surface of a sun. It is a perfect, smooth sphere. Any mountains on its surface are thought to be flattened by the impossible gravity to a height of mere inches. The side of any object closer to the star is now being pulled with significantly more force than the side farther away. This differential is a force known as a tidal force. It is the beginning of the body's deconstruction. The escape velocity has surpassed half the speed of light. There is no turning back. There is only down. Tidal forces. A question of scale. Tides are a familiar concept on Earth. They are the gentle rise and fall of the oceans, orchestrated by the moon's gravity. A tidal force is the asterisk difference in gravity across an object. The moon pulls on the near side of Earth more strongly than the far side, stretching the planet and causing the oceans to bulge. Now, replace the moon with a neutron star. And replace the Earth with the human body. The process would begin subtly. It would manifest as a sense of profound vertigo, a feeling of being pulled in two directions at once. Because the body is, the star's gravity is pulling on the feet with immensely more force than it is pulling on the head. The force of gravity diminishes with the square of the distance, and when the gravitational field is this intense, the few feet of a person's height become a vast and meaningful distance. At first, it would feel like a powerful strain. Joints would ache as ligaments are put under a tension they were never meant to endure. The spine would feel a pulling force, trying to separate each vertebra. As the fall continues, this strain would escalate. The bones themselves would be put under tension, stretched from both ends. There would be a series of pops and cracks as joints dislocate. The body would be dismantled, piece by the gradient of gravity. Even neutron stars are subject to these forces. In binary systems, their mutual gravity raises tides on their own surfaces, deforming crusts that are millions of times more rigid than steel. A body made of soft tissue and bone does not stand a chance. The stretching intensifies. Skin would be pulled taut and begin to tear. Muscle fibers would shred. Internal organs, no longer held in a stable torso, would be elongated and pulled apart. This is the physical reality of spaghettification. It is a term that sounds almost whimsical, but it describes a process of profound deconstruction. The body would be drawn out, extruded by gravity into a long, thin strand of biological matter. It is no longer a human being. It is a stream of organic material, miles long, raining down toward the surface of a dead star. And yet, this is only one part of the process. Radiation and magnetism, an environment of extremes. Long before tidal forces complete their work, the body would be subjected to an invisible storm of pure energy. Neutron stars are not cold. When formed, their internal temperature is around 1,000,000,000 degrees Kelvin. Even after thousands of years, the surface remains at a staggering 1,000,000 degrees. This extreme heat means the star radiates ferocious energy, not as visible light, but as X-rays and gamma rays. From hundreds of miles away, this radiation would pass through a ship's hull and through the body, as if it were not there. But each high-energy photon is a microscopic projectile, striking the atoms of the cells. The delicate structure of DNA would be shattered. The water within the cells would be heated past its boiling point. The body would be cooked from the inside out. There is no shielding that could protect against this. The heat is only part of the assault. Many neutron stars, known as magnetars, possess the most powerful magnetic fields in the universe, reaching a quadrillion Gauss, 1,000 trillion times stronger than Earth's. A body does not simply pass through such a field. It is fundamentally altered by it. At a distance of 600 miles, a field this strong would be powerful enough to affect the iron in the hemoglobin of the blood. Closer still, the field wages war on the structure of matter itself. Atoms, which consist of a nucleus surrounded by a cloud of electrons, would be grotesquely distorted. The electron clouds would be stretched and squeezed into long, needle-thin cylinders. The rules of chemistry would be erased. The covalent bonds that hold molecules together would become impossible. The substance of the body, proteins, fats, and carbohydrates, would simply dissolve, its molecular structures torn apart by the magnetic stress. The electrical impulses that constitute thought and consciousness would be instantly extinguished. If the star is also a pulsar, it adds another layer. A pulsar is a rapidly rotating neutron star that sweeps beams of intense radiation across space, like a cosmic lighthouse. Up close, this is not a gentle pulse. It is a high-energy blast, hundreds of times per second, each one contributing to the rapid and total vaporization of matter. Between the tidal forces, the radiation, and the magnetism, the end is a symphony of physics playing out in the final milliseconds. The impact. Assimilation into the core. What does it mean to touch the surface of a neutron star? The question itself is flawed. There is no recognizable object left to do the touching. The human form was erased miles above the surface. What arrives is a thin, superheated stream of subatomic particles, raining down at incredible velocity. The journey from a few miles out takes mere microseconds, and in that time, the infalling matter is accelerated to a significant fraction of the speed of light, perhaps 150,000 kilometers per second. This stream of particles encounters the surface. The outermost layer of a neutron star is theorized to be a solid crust of atomic nuclei, likely iron, crushed so tightly that the density is already 1,000,000 times that of gold. It is the strongest material in the universe. The impact of the particles that once constituted a body would release a monumental amount of energy, a brilliant flash of gamma rays erupting from the point of contact. But even this is just a surface event. Under the unimaginable pressure, the particles are instantly crushed and assimilated into the star. The protons and electrons in the atomic stream are forced to merge, becoming neutrons, just like the matter of the star itself. Deeper inside the crust, the physics becomes even more bizarre. Here, scientists theorize the existence of nuclear pasta, where nuclei are squeezed into strange, exotic shapes. Long spaghetti-like strands or flat lasagna-like sheets. Finally, at the core, the journey ends. Here, the density is so extreme that our understanding of physics breaks down. The core could be a superfluid of neutrons, a state of matter with zero viscosity. It might even be a soup of deconfined quarks, the fundamental particles normally locked inside protons and neutrons. The infalling mass, the very essence of the original matter, is absorbed into this final, unknowable state, adding an infinitesimal amount to the star's total mass and disappearing from the universe as a distinct entity forever. The journey is over. Matter has been stretched, irradiated, magnetized, vaporized, and crushed into a state that barely resembles its origins. It has been unwritten, its atoms recycled into the body of a dead star. The story of a neutron star is a stark and powerful illustration of the extremes that exist in our cosmos. These objects are not theoretical curiosities. Billions of them are scattered throughout our own Milky Way galaxy, spinning silently in the dark. They are the natural, inevitable result of gravity's relentless work, a demonstration of what happens when matter is pushed to its absolute limit. When we look up at the night sky, we see points of light that tell stories of creation and stability. But hidden among them are other stories, tales of violent transformation, extreme density, and physical laws pushed to their breaking point. The neutron star is a cosmic memento mori, a reminder that the universe is not designed for us. It is vast, indifferent, and capable of a power so profound it erases the very concept of an object. It is a testament to the fact that in the grand theater of the cosmos, some of the most wondrous things are best admired from a very, very safe distance. Holding a teaspoon of a neutron star would do this. Imagine a teaspoon, a simple, familiar object. Now, imagine in that spoon rests a substance so dense that it carries the weight of a mountain. But the sheer weight of this material is perhaps the least curious thing about it. Because the moment this tiny sample is lifted from the immense gravity of its home, it begins to unravel. And in that quiet unraveling, we can see the story of the universe's most fundamental rules. This is a journey to understand a cosmic remnant. A quiet echo of a violent event. We are talking about a neutron star. To understand the teaspoon in our hypothetical hand, we first have to travel across the cosmos and witness how such an object comes to be. It is a story that begins with a star, far more massive than our own sun. For millions or perhaps billions of years, this star lives its life. In its core, a furnace of nuclear fusion converts lighter elements into heavier ones. This process creates an outward pressure, a constant push against the relentless inward pull of the star's own gravity. For most of a star's existence, these two forces are in a state of delicate balance, what is known as hydrostatic equilibrium. The star is stable, a point of light in the darkness. But this balance cannot last forever. Eventually, the star's fuel begins to run low. The fusion that held gravity at bay starts to slow. The core begins to fill with iron, and for a star of this size, iron is an end point. Fusing iron does not release energy, it requires it. The furnace begins to cool. The outward pressure fades. And gravity, the patient, ever-present force, begins to win. The star starts to collapse. What happens next is one of the most powerful events in the known universe, a core collapse supernova. It is not a slow process. It is a sudden and profound change. The star's core, no longer supported, collapses in on itself. In less than a second, A region the size of a planet can be compressed to the size of a city. The temperatures and pressures reach levels that are difficult to comprehend, soaring to many billions of degrees. As the core collapses, the star's vast outer layers fall inward, crashing down upon it. They rebound off the newly formed, incredibly dense core in a catastrophic shockwave. This wave tears the star apart, sending its outer layers into space in a brilliant expansion of light that can briefly outshine its entire galaxy. This beautiful, expanding cloud of gas and dust is what we call a supernova remnant. We see them across the sky, quiet markers for the places where massive stars once lived. But what is left behind? For some of the most massive stars, the collapse is unstoppable, and a black hole forms. But for stars within a particular mass range, something else remains. Something that is, in its own way, just as extreme. The pressure of the collapse is so overwhelming that it rewrites the rules of matter. On Earth, atoms are mostly empty space, a tiny nucleus of protons and neutrons, with electrons orbiting at a great distance. In the core of a collapsing star, there is no more empty space. The force of gravity is so strong that it overcomes the forces that keep atoms apart. Electrons are pressed directly into protons. A negative charge and a positive charge merge, canceling each other out to create a new particle, a neutron. The core of the star becomes a super-dense sphere composed almost entirely of neutrons. This is where a neutron star gets its name. It is a city-sized atomic nucleus, an object so dense it bends the fabric of spacetime around it. This process is one of transformation. The star that ended its life gave birth to something new. And it is from this cosmic remnant, this stellar corpse, that we are going to hypothetically take our teaspoonful. The material is no longer ordinary matter. It has been crushed into a state that exists almost nowhere else. It is a substance born from the very limits of physics. Before we can even consider touching it, we have to appreciate the quiet violence that created it. This isn't just a spoonful of a star. It is a spoonful from the heart of a supernova. So, the supernova has faded, and what remains is one of the most extreme objects in the cosmos. A neutron star no longer generates heat through fusion. It is a stellar remnant, a cooling ember that will slowly release the immense heat of its birth over billions of years. But cooling is a relative term. A new neutron star can have a surface temperature of millions of degrees, far hotter than our own sun. And it is small, deceptively so. A typical neutron star contains about 1.5 times the mass of our sun, but it is compressed into a sphere only about 20 to 30 kilometers in diameter. Imagine taking our entire sun and crushing it down until it would fit inside the boundaries of a single city. This is the scale of compression we are considering. This leads to the property neutron stars are most known for, their density. The numbers are so large they become difficult to visualize. The density is comparable to that of an atomic nucleus itself. This has led some to describe a neutron star as a single, giant nucleus, held together not by nuclear forces, but by its own immense gravity. This is where we return to our teaspoon. A standard teaspoon holds about 5 cubic centimeters. Given the density of neutron star material, that single spoonful would have a mass of around 5 trillion kilograms. To put it another way, it would be like holding the mass of 900 Great Pyramids of Giza in a small spoon. While the exact number changes depending on where in the star the sample is taken, the conclusion is the same. It is an amount of mass that does not seem to fit within such a small space. The weight is one thing, but the gravity it creates is another. The surface gravity of a neutron star is about 200 billion times stronger than the gravity on Earth. If you could stand on its surface, you would be instantly flattened into a thin layer of atoms. Even the mountains on a neutron star, ripples in its crust, are thought to be only a few centimeters high. Any taller, and the star's own gravity would pull them flat. This gravity also bends light, an effect called gravitational lensing. If you were looking at a neutron star, light from its back surface would be bent around into your line of sight, allowing you to see part of the other side. The escape velocity, the speed needed to break free from its gravity, is more than half the speed of light. And then there is the spin. Because of the conservation of angular momentum, the same principle that makes a spinning ice skater speed up when they pull their arms in, a collapsing star rotates faster and faster. A star that once rotated every few weeks might now rotate hundreds of times per second. The fastest known neutron star spins 716 times every second. But what holds this object together? Why does it not collapse further into a black hole? The answer is a quantum mechanical principle called neutron degeneracy pressure. The neutrons are particles called fermions, and a fundamental rule of the universe, the Pauli exclusion principle, states that no two identical fermions can occupy the same quantum state at the same time. In essence, the neutrons are resisting being compressed any further. They are pushing back against gravity with a powerful quantum force. It is not thermal pressure, like in a living star. It is a pressure that arises from the nature of the particles themselves. They are packed as tightly as the laws of physics allow. This outward pressure is in a tense equilibrium with the inward crush of gravity. It is the only thing keeping the star from becoming a black hole. This is the object of our thought experiment. A city-sized sphere of nuclear density matter, held in a delicate balance between total gravitational collapse and quantum repulsion. It is stable only because all the forces acting on it are at their absolute limit. And now, we are going to imagine reaching in with our spoon and removing a piece of it. If this kind of quiet journey to the edges of physics helps you unwind, consider subscribing to the channel. We are only just beginning to explore what happens when this balance is disturbed. So, we have our destination. A spinning, super-dense object of immense gravity. And we have our task, to collect a single teaspoonful of its substance. The challenges of such a task help us appreciate the environment we are dealing with. First, you would have to get there. As a hypothetical, indestructible ship approached the neutron star, the first problem would be the tidal forces. On Earth, the moon's gravity creates tides because it pulls more strongly on the side of the planet facing it. Now, imagine that force amplified by billions. The gravity pulling on the front of the ship would be immensely stronger than the gravity pulling on the back. This difference would stretch the ship into a long, thin stream of atoms, a process called spaghettification. Let us assume our ship can counteract this. We hover just above the surface. We would find a solid crust made of iron nuclei and other heavy elements, pressed into a crystalline lattice estimated to be billions of times stronger than steel. It is also incredibly hot, 1,000,000 degrees even for an old star, flooding the area with X-rays and high-energy radiation. And then there is the magnetic field. As the original star collapsed, its magnetic field was crushed and amplified, becoming trillions of times stronger than Earth's. In such a field, the very structure of atoms is distorted. Electron orbitals, normally spherical, are stretched into thin needles. Chemistry as we know it would cease to function. Let's imagine we have a ship and a spoon that can withstand all of this. A robotic arm lowers the spoon and chips off a tiny, 5 cubic centimeter piece of the crust. The moment it is free, this sample has a mass of trillions of kilograms. The spoon begins to pull away from the neutron star. And this is the most important part of our story. As the spoon moves away, the gravitational pull on the material inside it begins to decrease. For its entire existence, this piece of matter has been defined by pressure. The immense pressure of the star's gravity crushing it from the outside, balanced by the neutron degeneracy pressure pushing out from within. It was a perfect, stable equilibrium. But now, we have removed one half of that equation. The external, crushing gravity is fading with every meter the spoon travels. The internal, quantum pressure, however, is still there. The neutrons are still pushing away from each other. The force holding them in their impossibly small space is disappearing. Inside our hypothetical spoon, we are no longer holding a stable piece of a star. We are holding something that can no longer exist in its current form. The conditions that made it have been removed, and a process of transformation is about to begin. The spoon is clear of the star. For a brief moment, all is calm. But inside the small speck of matter, a fundamental change is starting. The forces of nature are about to reassert themselves. The problem is the imbalance. The external gravity is gone, but the internal neutron degeneracy pressure is not. It is like holding a massive spring compressed to the size of a sugar cube and then suddenly letting it go. The material begins to expand, driven by this raw, quantum repulsion. It flies apart at a significant fraction of the speed of light. But that is only the beginning. As the material expands and the pressure drops, another fundamental process begins: beta decay. A free neutron, when not bound inside an atomic nucleus, is not stable. It will naturally decay, with a half-life of about 10 minutes, into a proton, an electron, and an antineutrino. Inside the neutron star, the immense pressure prevented this. Any decay was immediately reversed. But now, with the pressure gone, the process can start. Across our entire sample, trillions upon trillions of neutrons begin to decay at once. Each decay releases a small amount of energy, but when multiplied by the sheer number of neutrons in our spoonful, the total energy release becomes staggering. This creates a cascade of instability. The initial expansion lowers the density, which allows beta decay to start. The beta decay releases enormous amounts of energy, which heats the material to billions of degrees and accelerates the expansion even further. So what would we see if this happened in empty space, a safe distance away? In the first microseconds, the speck of matter would erupt in a flash of gamma rays as the neutrons decay. A flood of electrons and antineutrinos would stream away at nearly the speed of light. As neutrons decay into protons, these new protons would begin capturing other free neutrons. This is known as the R process, or rapid neutron capture process. It begins to forge heavy elements. The expanding cloud is no longer just neutron matter. It is an alchemical furnace, creating a spray of radioactive isotopes of every element, from iron all the way up to gold, platinum, and uranium. Astronomers now believe that the collision of two neutron stars is the primary source of these heavy elements in the universe. Our little teaspoon is now reenacting that cosmic genesis in miniature. In less time than it takes to blink, our teaspoonful of star stuff has become an expanding fireball many kilometers in diameter, glowing with the light of 1,000 suns and seeding the space around it with freshly made precious metals. We started with a simple question. What happens when you take a piece of a neutron star away from its home? The answer is a quiet paradox. You cannot. The moment you remove it from the gravity that gives it form, it ceases to be neutron star material. It becomes something else. It unbecomes. It reverts from its state of impossible compression back into normal matter, and the energy released in that transition is immense. We have not just scooped a spoonful of a star. We have simply allowed a piece of the universe to return to a more stable state, and witnessed the energy that process releases. We have talked about the physics. Now, let's consider the consequence. What is the actual energy yield of this transformation? Calculating the exact energy is complex, but conservative estimates suggest the process releases around 10 to the power of 28 to 10 to the power of 29 joules. To offer some perspective, the asteroid impact that led to the extinction of the dinosaurs is estimated to have released about 10 to the power of 23 joules. Our single spoonful, then, represents an energy release tens of thousands of times more powerful. If such an event were to happen on the surface of our planet, the consequences would be on a planetary scale. It would not be an explosion in the conventional sense, but a release of energy so immense it would fundamentally alter the environment. The initial flash of light and radiation would be brighter than the sun and would sterilize the surface of the planet. The shockwave from the expanding matter would create a fireball that would engulf a vast area, vaporizing everything inside and creating a crater hundreds of kilometers across. The blast wave would travel around the globe in minutes, and the heat would boil the upper layers of the oceans. The planet itself could be affected, with the event triggering earthquakes and volcanic activity on a global scale. In short, it would be an extinction event that would render the planet uninhabitable for millions of years. And this all comes from a single teaspoon, a tiny sample of matter from a place where the rules of our world do not apply. It serves as an ultimate, quiet warning. There are forces in the universe so concentrated that they operate on a scale we are not equipped to handle. The laws of physics that allow for the existence of a neutron star also decree that such matter can only exist in that environment. By removing it, we are not just moving an object. We are breaking a fundamental balance. The result is not just an explosion, it is the universe decisively correcting an imbalance. It is a reminder that some things are meant to be left alone. So, what would happen if you held a teaspoon of a neutron star? The truth is, you never could. But by exploring why, we take a journey to the very edge of physics. It is a tale of stellar birth and death, of forces that compress reality, and of the quantum rules that push back. It demonstrates that the stability of matter, something we take for granted, is not a given. Our world exists in a gentle, low-energy corner of the cosmos. But out there, in the hearts of dead stars, matter exists in a state of barely contained potential. The decompression of neutron star material is more than a thought experiment. It is a profound lesson in cosmic humility. It shows that the universe is not required to be safe or intuitive. The same processes that forged the gold in our world are capable of unleashing energy on a scale that could reshape a planet in an instant. We began with a simple object, a teaspoon, and filled it with one of the most complex substances imaginable. In doing so, we did not unleash a demon. We simply observed the fundamental forces of the universe, all at once, in a final, spectacular, and transformative display. It is a reminder that we are a fragile species on a fragile planet, in a universe that is far more powerful, and far stranger, than we often imagine. Exploring these cosmic extremes helps us understand our own place in the universe. If you would like to continue diving into these questions, feel free to let us know in the comments what cosmic mystery you want us to explore next. Why a neutron star is scarier than a black hole. When we think of the most absolute ends in the cosmos, we often picture a black hole. A quiet, inescapable abyss. The final word in cosmic solitude, a one-way journey into mystery. It has settled in our minds as the ultimate unknown, an object so dominant it consumes light itself. But what if I told you there's another place in the universe, a place where you wouldn't have time to contemplate the mystery? A place where gravity, radiation, and matter itself are so extreme, they make the quiet passage across an event horizon feel almost gentle by comparison. Today, we're going to take a quiet journey toward one of these objects. And we're going to explore why this small, dense remnant of a star might represent a more immediate and visceral kind of finality. The familiar idea of a black hole is unsettling because of what it represents. A slow, graceful folding of space-time, a point of no return. We are conditioned to feel a sense of unease about its silent, invisible boundary. But a neutron star offers something different. Not a mystery to fall into, but a physical reality so intense it challenges our understanding of matter. It's not about being erased from space-time. It's about being physically unmade by forces we can measure and describe, taken to their most extreme conclusion. We're going to look at these incredible objects, from their surfaces of searing light to their strange, nuclear pasta cores. And by the end, we might see that while a black hole is a cosmic question, a neutron star is a physical answer. Before we explore this other path, it's worth spending a moment with the black hole. It has earned its place in our minds for a reason. Its character is not defined by violence, but by how it fundamentally changes the reality we think we know. The defining feature of a black hole is its event horizon. It isn't a surface you can touch. It's an invisible line, drawn in spacetime by gravity. Once you cross it, your future holds only one possible destination: the singularity at the center. The physics of this are as elegant as they are absolute. Inside the event horizon, the direction toward the singularity is no longer a direction in space, but a direction in time. Just as you cannot stop moving toward your own future, once across that threshold, you cannot stop moving toward the black hole's core. Escape is a temporal impossibility. Even light is held still. The way this journey is said to end is through spaghettification. This is a quiet consequence of tidal forces, the difference in the pull of gravity from one point to another. As you fall toward a smaller, stellar mass black hole, the gravity on the part of you closer to the center would be significantly stronger than the gravity on the part of you farther away. This difference would stretch your body, elongating it into a thin stream of atoms. It's a strange, almost abstract way to be undone, pulled apart by the shape of spacetime itself. For a supermassive black hole, the kind at the center of a galaxy, the event horizon is so vast and the gravitational slope so gentle that you could drift across it without noticing a thing. You would be lost, but you wouldn't know it yet. The spaghettification would come much, much later, deep inside. This is a quiet, existential unease. It's the feeling of being irrevocably lost, of drifting past a point of no return into a fate where the laws of physics themselves cease to offer clarity. You don't hit a wall. You simply enter a place where all paths lead to the same unknowable end. The nature of a black hole is philosophical. It's the ultimate trap, but it's a slow descent into that abyss. Now, let's talk about something that offers no such gentle passage. Our other destination today doesn't have an event horizon. It has a surface you could, in theory, approach, if you weren't immediately and completely undone in a dozen different ways. Meet the neutron star. A neutron star is what remains after a massive star, one somewhere between about 8 and 25 times the mass of our Sun, ends its life in a spectacular burst of light called a core collapse supernova. Throughout its life, a star exists in a state of perfect balance, gravity trying to crush it, and the outward pressure from nuclear fusion pushing back. For millions of years, these forces are in equilibrium. But when a massive star runs out of fuel, that outward pressure vanishes. With nothing to hold it up, gravity prevails. The star's core, which might already contain more mass than our entire Sun, collapses inward in a fraction of a second. The pressure becomes so immense that the very structure of matter gives way. Protons and electrons are forced to merge, becoming neutrons. This process releases a flood of neutrinos that blasts the star's outer layers into space, creating the supernova we see from light years away. What's left is a neutron star. An object with about 1.5, sometimes up to 2.5 times the mass of our Sun, crushed into a sphere just 20 kilometers, or 12 miles, across. That's the mass of a star contained within the footprint of a city. This isn't just a dense object. It's a new state of matter, a city-sized atomic nucleus held together by gravity. Forget the abstract singularity of a black hole. A neutron star is a tangible, physical object. And it is in the details of its physics that we find a different kind of ending, one that is immediate, overwhelming, and deeply personal. Approaching a neutron star is not a quiet drift across an invisible line. It is a journey into a region where each step closer introduces a new, and more efficient, way for matter to be disassembled. A black hole's finality is its mystery. A neutron star's is its sheer, overwhelming physical presence. Let's begin with gravity. The gravitational field at the surface of a neutron star is around 200 billion times stronger than it is on Earth. It's a number so large it's hard to grasp. If you could somehow arrive and stand on its surface, the concept of standing would lose all meaning. Any object, from a spaceship to a person, would be flattened into a thin layer of plasma spread across the crust. But you would never reach the surface intact. Just as with black holes, the tidal forces are extreme. Because a neutron star has a solid surface, however, these forces feel much more immediate. Long before you arrived, the difference in the pull of gravity on your head versus your feet would become so great it would simply pull you apart. This isn't the slow stretching of spaghettification over thousands of kilometers. This is being swiftly unmade by a gravitational gradient that strengthens with brutal speed. An object dropped from just 1 meter above the surface would impact at over 1,000 kilometers per second, releasing its energy with an unimaginable finality. Its atoms wouldn't just scatter. They would be driven into the crust with such force that they would become part of the star itself. The gravity here is so strong it bends light around the star, allowing you to see parts of the back from the front. It's a dizzying, disorienting distortion of space, caused by a field that wants to crush everything into its simplest form. If the gravity didn't unmake you, the heat and radiation would. A young neutron star is born with a core temperature of trillions of degrees. While it cools, its surface remains punishingly hot for millions of years, glowing not in visible light, but in a constant, searing bath of high-energy X-rays and gamma rays. To approach a neutron star would be to fly into a silent storm of radiation so intense it would sterilize a spacecraft and shred the molecular bonds essential for life long before you got close. You would be gently, but completely, cooked and irradiated. This isn't just heat. Many neutron stars are also pulsars, rapidly spinning objects with powerful magnetic fields. These fields create beams of particles and radiation that sweep through space like a cosmic lighthouse. If one of these beams were to cross your path, you would be struck by a focused blast of energy that could strip a ship apart. The density of a neutron star is also difficult to comprehend. A single teaspoon of its material would weigh billions of tons. A sugar cube-sized piece would weigh as much as a mountain. This is what happens when gravity overcomes the space inside atoms, crushing them down to a substance made almost entirely of neutrons, packed together as tightly as physically possible. Just below the solid crust, this extreme pressure creates what may be the strongest material in the universe, nuclear pasta. Here, the forces that hold atomic nuclei together and the forces that push them apart are locked in a titanic struggle. This competition arranges the neutrons and protons into strange, complex shapes that, in simulations, resemble different kinds of pasta. Deeper in, you first find spherical clumps, which physicists call the gnocchi phase. As pressure mounts, these are squeezed into long rods, known as the spaghetti phase. Deeper still, they flatten into sheets, creating the lasagna phase. This isn't just a curious naming convention. Nuclear pasta is thought to be 10 billion times stronger than steel. To break it would require an almost impossible amount of force. To collide with this layer would be like striking a fundamental property of the universe that simply refuses to yield. As if that weren't enough, some neutron stars amplify magnetism to a cosmic scale. These are the magnetars. As the star's core collapses, its magnetic field is compressed and intensified to an almost unimaginable degree. A typical neutron star's field is 1 trillion times stronger than Earth's. A magnetars can be 1,000 times stronger still, making them the most powerful magnetic objects we know of. From a distance of 1,000 kilometers, a magnetar's field is strong enough to overwhelm the bonds that hold matter together. The field distorts the electron clouds of atoms, stretching them into thin cylinders. Normal chemistry becomes impossible. The iron in your blood would be pulled from your cells. The faint bioelectric signals that carry your thoughts would be catastrophically overridden. You would cease to be a collection of molecules and become a cloud of magnetically aligned particles. Finally, there is the spin. Because of the conservation of angular momentum, as the star's core collapses from something vast to the size of a city, its rotation speeds up dramatically. Young neutron stars can spin hundreds of times per second. The fastest known, PSRJ 174824446 AD, rotates 716 times every second. Its equator moves at nearly a quarter of the speed of light. So, let's recount the approach. You are simultaneously being pulled apart by tidal forces, irradiated by a silent storm of X-rays, and disassembled by a magnetic field that rewrites the rules of chemistry. And if any piece of you were to survive all that, it would impact a surface made of the strongest material in the known universe. Now, let's put it all together. Let's imagine a final journey to each of these cosmic remnants. Which ending feels more profound? The fall into a black hole begins in silence. From a distance, it is a perfect circle of black against the stars. As you draw closer, the light from behind it bends and warps. You are witnessing the curvature of space-time. You feel no pull different from any other massive object. You are simply in orbit. You decide to go in. The journey is subtle at first. As you cross the event horizon of a large black hole, nothing changes. There is no sign, no alarm. One moment you are in the observable universe, the next, you are not. You can still see the stars outside, but no one can see you. A quiet realization begins to dawn. You are past the point of no return. In your own frame of reference, your time is short. The stretching from the tidal forces intensifies, not as a violent shredding, but as an inexorable, irresistible elongation. Your death is a slow, bizarre dissolution into a stream of particles. It is an end defined by a physics puzzle, a surrender to the warped geometry of the cosmos. It's lonely, absolute, and profoundly strange. The journey toward a neutron star is an assault on the senses from the very beginning. Long before you can see it as more than a point of light, your instruments would tell a story of overwhelming energy. The radiation is a lethal storm. Closer still, the magnetic field of a magnetar would take hold. Your ship's electronics would fail. The atoms in your own body would be stretched and distorted. Your thoughts would cease as the electrical impulses in your brain are scrambled. This all happens far from the star itself. Let's imagine you are somehow shielded from this. Now you must contend with the gravity. The tidal forces are not subtle, they grip you and pull you apart. But for the sake of the journey, let's say a single piece of you continues on. It accelerates to a fraction of the speed of light in moments. It is superheated by the ambient temperature. And then, it makes contact. It doesn't land. It impacts the surface with the energy of a bomb. The surface itself is a crystalline lattice of iron, and below it, the incomprehensibly strong nuclear pasta. Your remaining matter is not just broken apart, but its constituent particles are crushed and absorbed into the stellar mass. You become one with the star. The comparison is a quiet one. A black hole offers an end of isolation and mystery, a descent into the unknown. It is unsettling because of what we don't know. A neutron star offers an end of pure, unadulterated violence. It is unsettling because of what we do know. Every force we understand, gravity, electromagnetism, the strong nuclear force, is turned up to a level that is actively hostile to matter as we know it. A black hole is a trapdoor in space-time. A neutron star is a blast furnace, a particle shredder, and a gravitational pulverizer, all in one. The unease of black holes comes from how they challenge our intuition about the universe. They are places where space and time become so warped that our ideas of place and future break down. The event horizon is a boundary of knowledge itself. Beyond it lies a singularity, a point where our equations fail. The feeling is existential. It is the quiet fear of non-existence, of being erased from reality. A black hole is unsettling because it represents the ultimate unknown. The unease of a neutron star is different. It's not about the unknown. It's about taking everything we know about physics and pushing it to its most extreme conclusion. A neutron star doesn't break the laws of physics. It is the ultimate expression of them. We understand gravity. A neutron star shows us gravity so powerful it flattens matter to a subatomic smear. We understand magnetism. A neutron star shows us magnetism so strong it tears atoms apart from 1,000 kilometers away. We understand temperature. A neutron star shows us a surface so hot it vaporizes matter with a blast of X-rays. We understand density. A neutron star shows us matter so dense that colliding with it is like hitting a wall that is, for all purposes, infinitely hard. This is an unease of the known. It's the feeling of being subjected to comprehensible forces at an incomprehensible intensity. There is no mystery to what a neutron star will do to you. It will crush you, burn you, irradiate you, and tear you to pieces. While a black hole's event horizon is a point of no return, a neutron star's entire vicinity is a keep out zone, enforced by the most violent forces in the cosmos. A black hole is a ghost that haunts space-time. A neutron star is a physical monster. For decades, the black hole has held a singular place in our cosmic story. It's the silent predator, the symbol of oblivion. Its mystery is its power. But as we've journeyed toward its smaller, denser cousin, a different kind of finality has emerged. It's the finality of a place where gravity is a physical hammer, not just a geometric curve. It's the hellscape of a surface heated to millions of degrees, bathing its surroundings in lethal radiation. It is the sheer violence of a magnetic field that can dissolve your molecular bonds from across a solar system. A black hole ends your journey with spacetime itself, with a quiet, inexorable fall into an abyss of broken physics. A neutron star ends your journey with everything else. It is a blitzkrieg of heat, pressure, radiation, and magnetism. It is not an abyss you fall into. It is a wall you slam against, a wall that embodies the most extreme physical forces the universe can muster. So the next time you look up at the night sky and contemplate the strange destinations hidden in the dark, remember this. While black holes may be the great unknowns of the cosmic machine, neutron stars are the physical certainties. They are the roaring, spinning, blazing remnants of stellar death. And they prove that the most profound things in the universe aren't always the ones we can't see, but the ones whose brutal reality is all too clear. If you found this journey into the heart of these cosmic objects as fascinating as I did, consider subscribing and hitting that notification bell. We dive into these kinds of concepts every week. Let me know in the comments which cosmic object you find more compelling, and why. You can also support the channel directly through Patreon, where you get access to exclusive content and can join our community on Discord to discuss these topics further. Humanity's impossible plan to visit a neutron star. In the quiet, sprawling spaces of the universe, there are objects that exist at the very edge of our understanding. We have names for them: black holes, quasars, neutron stars. But these are just labels for things so far outside our daily experience that they feel more like ideas than places. Among them, there is one that is perhaps the most fascinating, and the most forbidden, destination we have ever imagined: the neutron star. It is what remains of a star, a city-sized atomic nucleus floating in the void, where the fundamental rules of the universe are pushed to their breaking point. To visit one, even to get close, is a journey into forces we were never meant to survive. And yet, we are deeply curious. The question that drives us is not if we can go, but how we can possibly study a place we can never touch. This is the story of that quiet, impossible plan. A story of how we hope to understand a thing we can never approach. If you find this kind of calm exploration into the cosmos helps you unwind, consider liking the video and subscribing. And wherever you are right now, whether it's a quiet room or a busy city, Feel free to share where you're watching from in the comments below. Imagine, for a moment, a journey to the ultimate destination. You move through the black, toward a tiny, distant point of light. As you draw nearer, you realize it is not a star like our sun, but something far stranger. To reach out and touch it would be to be undone. The moment your fingertip made contact with its surface, the very atoms of your body would be dissolved in a release of energy that would make the core of our sun seem like a cool day. The gravity is so absolute, in some cases, hundreds of billions of times stronger than Earth's, that you would be flattened into a thin layer of particles before a single nerve could register what was happening. This is not just a destination, it's a physical paradox, a place where matter itself becomes something else entirely. So, if a physical visit is impossible, how do we plan to unlock its secrets? Before we can understand the quiet ingenuity of studying a neutron star, we must first appreciate the object we are dealing with. A neutron star is not born in peace. It is the result of the violent collapse of a massive star, one at least 8 times the mass of our own sun. For millions of years, that star exists in a delicate balance. The outward push of nuclear fusion in its core holds back the inward crush of its own gravity. But eventually, the fuel runs out. The fire goes out. And gravity, the most patient force in the cosmos, finally wins. In less than a second, the star's core collapses. The outer layers, with nothing left to hold them up, come crashing down at nearly a quarter of the speed of light. They hit the now impossibly dense core and rebound, triggering a supernova. For a few weeks, this single dying star can outshine its entire galaxy, scattering the heavy elements needed for life across the cosmos. But left behind in the quiet aftermath is the core, the remnant, the neutron star. During the collapse, the pressure is so great that it overcomes the forces that keep atoms as we know them apart. Electrons are forced into protons, merging to form neutrons. The entire core, with a mass up to twice that of our sun, is compressed into a sphere no larger than a city, perhaps just 12 to 20 kilometers across. This creates a state of matter so alien it's difficult to describe. We call it neutronium. The density is simply beyond easy comparison. Imagine taking all the oceans, mountains, and cities of our entire planet and crushing them down to the size of a sugar cube. A single teaspoon of neutron star material would weigh something like 10 billion tons, more than Mount Everest. If you could somehow place that teaspoon on Earth, it wouldn't just sit there. It would fall through the spoon, through your hand, through the ground, and plummet toward the Earth's core as if our planet were made of mist. This is matter on the absolute edge of becoming a black hole, the final point from which nothing, not even light, can escape. This density creates other extreme properties. As the star's core collapses, its spin speeds up, just as an ice skater spins faster when they pull their arms in. A newborn neutron star can rotate hundreds of times per second, its surface moving at a significant fraction of the speed of light. Then there is its magnetic field. Compressed by the collapse, it becomes trillions of times more powerful than Earth's. Some neutron stars, called magnetars, have the strongest magnetic fields known, so powerful they can warp empty space and cause starquakes on the surface, releasing bursts of energy that can be detected across the galaxy. On December 27, 2004, a flare from a magnetar 50,000 light-years away was so strong that it measurably affected Earth's upper atmosphere. This object is not just a dead star. It is an active, dense, and magnetic engine, a place where every fundamental force is turned up to a level that means certain dissolution for any visitor. So, let's imagine a journey, not because we could ever take it, but to understand the forces at play. What would happen to a probe on a journey to a neutron star? The challenges begin long before arrival. Tens of thousands of kilometers out, while the star is still a distant point of light, you enter a region of intense radiation. Neutron stars are incredibly hot, with surface temperatures in the millions of degrees, and they release lethal amounts of X-rays and gamma rays. Any ordinary spacecraft would be sterilized, its electronics fried in an instant. If the target is a pulsar, a spinning neutron star that sweeps beams of radiation through space like a cosmic lighthouse, passing through that beam would be like standing in front of an astrophysical particle accelerator. But imagine our probe has some sort of impossible shield. The journey continues. Now it must face the magnetic field. For a magnetar, this field is so strong it changes the rules of chemistry itself. At a distance of thousands of kilometers, it would induce powerful currents in any metal, tearing the probe apart piece by piece. It would distort the very atoms of the probe, warping the electron clouds that define them. Matter as we know it would cease to function in a familiar way. Even if it survived this, the final and most fundamental force awaits: gravity. Specifically, the tidal forces. As the probe gets closer, the gravitational pull on the side nearest the star becomes unimaginably stronger than the pull on the far side. This difference in force, even over a small distance, begins to stretch it. Scientists have a quiet, descriptive name for this process: spaghettification. The probe would be pulled apart, first into pieces, then into a long, thin stream of atoms spiraling down toward the surface. And what if, by some miracle, a single atom from our probe reaches that surface? It wouldn't be a landing. It would be an impact at a significant fraction of the speed of light, releasing so much energy it would trigger a thermonuclear reaction. The remnants of our probe would become a brief flash of gamma rays, its mass absorbed into the star. It would not just be destroyed, it would become part of the neutron star. The destination is not just dangerous there. Its very substance is incompatible with our corner of the universe. If we could magically scoop up a teaspoon of it and bring it to Earth, freed from the immense gravity, the material would expand violently, releasing the energy of a massive explosion. Faced with such a complete and certain end, the logical question is, why think about it at all? Why are we so drawn to an object that seems designed to erase anything that comes near it? The answer is simple. The same properties that make neutron stars so hostile also make them one of the greatest physics laboratories in the universe. Inside a neutron star, matter exists at densities we can never replicate on Earth. Understanding what happens to matter under these conditions is one of the great quests of physics. Do the neutrons remain a tightly packed fluid? Or does the pressure become so great that they break down into their constituent quarks, forming an exotic quark soup? We have theories, but neutron stars are the only place to test them. They hold clues to the fundamental nature of matter itself. Their immense gravity also makes them perfect places to test Einstein's theory of general relativity. Gravity around a neutron star is so strong that it visibly warps spacetime. Light bends as it passes by, and time itself slows down. By observing these effects, we can test our understanding of gravity in ways that are impossible in the much gentler environment of our own solar system. The ultimate reason we study them is because it is in our nature to explore, to push the boundaries of our knowledge. Neutron stars represent a place where our theories of the very large, gravity, and the very small, particle physics, meet. To turn away from them simply because they are unreachable would be to accept that some parts of the universe are fundamentally unknowable. And that is something humanity has always quietly refused to do. The quest is not about survival, it is about understanding. So, the plan to visit a neutron star is not about a physical journey. It is a plan of observation, of deduction, of listening to the quiet messages of the cosmos from a safe distance. Our probes are not armored starships, but remarkable telescopes and detectors, each designed to capture a different piece of the story. This is our toolkit for exploring the impossible. Our first and most important tools are our telescopes. But you cannot simply point an ordinary telescope at a neutron star and see very much. They glow not in visible light, but in high-energy X-rays. This means we have to send our observatories into space, above Earth's protective atmosphere. Telescopes like NASA's Chandra X-ray Observatory have given us beautiful images of the superheated gas around neutron stars. But for the next step, we needed a dedicated instrument. That instrument is NICER, the Neutron Star Interior Composition Explorer. Attached to the International Space Station, NICER is less like a camera and more like a sensitive timer. It measures the arrival of every single X-ray photon from a neutron star with a precision of less than 100 nanoseconds. This allows scientists to do something remarkable. As a pulsar spins, hot spots on its surface sweep past our line of sight, creating a pulse of X-rays. NICER measures the exact shape of this pulse. Because the neutron star's gravity is so strong, it bends the path of the light, allowing us to see the hot spot even as it rotates onto the far side of the star. By analyzing how the light is bent, scientists can work backward to calculate the star's mass and its radius with incredible accuracy. Knowing both of these things allows physicists to narrow down the theories of what matter looks like in such an extreme state. In a very real sense, NICER is mapping the surface of these distant worlds from hundreds of light years away. For all their power, telescopes that see light only tell part of the story. A true revolution in studying the unreachable came with our ability to detect a completely different kind of signal: gravitational waves. On August 17, 2017, the LIGO and Virgo observatories detected a ripple in spacetime. The signal, named GW 170817, was different from previous detections. It was the signature of two neutron stars spiraling into each other. Just 1.7 seconds after the gravitational wave arrived, a gamma-ray telescope detected a burst of light from the same patch of sky. An alert went out to observatories around the world. Within hours, telescopes turned to the source galaxy, NGC 4993, about 130 million light-years away, and saw a new point of light that wasn't there before: the afterglow of the collision, an event called a kilonova. For the first time, we had felt and seen the same distant event. The gravitational waves told us about the masses of the stars and the physics of the merger. The light, observed by telescopes like Hubble and later the James Webb Space Telescope, allowed us to watch the creation of heavy elements. The debris from the kilonova was rich in newly made gold and platinum, confirming that these collisions are a primary source of the universe's heaviest elements. GW 170817 was the ultimate remote observation. We didn't need to go there. The event's light and its gravitational echo traveled for 130 million years, delivering a detailed story about stellar alchemy and the limits of matter right to us. While our current tools are powerful, our curiosity continues to grow. We want to get a clearer picture. The nearest known neutron star is still hundreds of light years away, a journey of millions of years with today's technology. And the environment remains just as hostile. So, what does the future of the impossible plan look like? It does not involve building a stronger ship. Instead, it involves making our remote senses even sharper. The future of visiting a neutron star is about smarter, more sophisticated ways of listening. First, we can build better eyes. Future telescopes will be able to survey the sky more efficiently, finding more of these neutron star mergers and building a larger collection of data. Second, we are developing new ways to feel. The sensitivity of gravitational wave detectors is constantly being improved, allowing them to register events from farther away and with greater detail. Some research even suggests we might be able to perform a kind of seismic survey from light years away by studying the subtle vibrations on a neutron star's surface. And what about actual probes? While a direct mission remains in the realm of imagination, the technology we are developing has other uses. One experiment successfully showed that pulsars can be used for autonomous spacecraft navigation, a kind of galactic GPS. For now, our most practical way of visiting a neutron star is right here on Earth, inside our supercomputers. Scientists can simulate the merger of two neutron stars in great detail. By comparing these simulations to real observations, we can refine our theories and get an ever clearer picture. In a way, we are already there, exploring these worlds through the language of mathematics and code. The plan to physically visit a neutron star is, and will likely remain, impossible. The gravity, the radiation, the magnetism, every part of its existence is a fundamental barrier. But our quest for knowledge has never been limited by what we can touch. The impossibility of the journey has forced us to become more clever. We cannot walk on its surface, so we learn to map it with X-rays. We cannot survive its collisions, so we listen for their gravitational echoes from 130 million light-years away. We cannot send a ship, so we send our minds, encoded in simulations that run on our most powerful computers. The dream of visiting a neutron star is not about planting a flag. It is about understanding the universe at its most extreme. It is a quiet testament to the curiosity that drives us to explore, even when the destination is a place we can never go. To touch a neutron star may be the end of a journey. But studying one from afar, we are discovering, is just the beginning of our understanding. If you enjoyed this journey to the edge of what's possible, let us know in the comments below. What impossible destination or cosmic enigma should we explore next? Your final second touching a neutron star. You are about to do something impossible. In the quiet of space hangs a sphere, no bigger than a city, yet it holds more mass than our sun. You reach out to touch its surface, which looks perfectly smooth. This will be the last thing you ever do. Before your own nerves can signal that something is wrong, a force beyond any earthly comparison will unmake you, atom by atom. This is a journey into your final second touching a neutron star. What you are looking at is not a planet. It is not a star in the way we usually understand them. It is a ghost. It is the hyper-dense, collapsed corpse of a massive star that died in a supernova. What's left behind is an object of such profound density that it challenges our everyday understanding of reality. These objects pack more mass than our sun into a sphere that would fit comfortably within the boundaries of a major city, just over 20 kilometers across. The material is so compressed that a single teaspoon of it would weigh billions of tons, as much as a mountain. The reason for this mind-bending density lies in what a neutron star is made of. It is, for all practical purposes, a giant atomic nucleus. In the matter you and I are made of, atoms are almost entirely empty space. A tiny, dense nucleus of protons and neutrons is surrounded by a vast, lonely cloud of orbiting electrons. The forces between these electrons keep atoms apart, creating the illusion of solidity. It is the only reason the floor holds you up, the only reason you do not fall right through it. But in a neutron star, that illusion has been broken. The gravitational collapse is so complete, so final, that the empty space within atoms has been squeezed out of existence. The immense pressure has forced electrons and protons to merge, creating a star made almost entirely of neutrons, packed together as tightly as the laws of physics will allow. It is matter at its absolute limit, the densest possible object in the universe that is not a black hole. And you are about to touch it. This journey into your final moments is not just a tale of destruction. It is a voyage to the very edge of physics, to a place where the rules that govern our world are pushed to their breaking point. The cosmic ghost, the birth of a monster. Before we arrive at the final, catastrophic second, we have to understand where such an object comes from. Neutron stars are born from fire and death. They are the tombstones of giants. It all begins with a star far more massive than our own sun, a star at least 8 times its mass. For millions of years, this stellar behemoth burns through its nuclear fuel. It is a colossal fusion reactor, forging lighter elements into heavier ones in its core. Hydrogen becomes helium, helium becomes carbon, and so on up the periodic table. Each stage of this process releases a tremendous amount of energy. This outward push of energy from fusion is what holds a star up, fighting a constant battle against the inward crush of its own gravity. For most of a star's life, these two forces are locked in a delicate equilibrium. But this balance cannot last. Eventually, the star's core creates iron. And with iron, the star's fate is sealed. Fusing iron into heavier elements does not release energy, it consumes it. The furnace at the heart of the star suddenly runs out of fuel. The outward push of energy stops, and gravity, the patient, relentless force, wins a sudden and catastrophic victory. In less than a second, the star's core collapses. The outer layers, once held at a distance, come rushing inward at a fraction of the speed of light. Temperatures and pressures skyrocket to unimaginable levels, reaching over 5 billion Kelvin. The core becomes so dense that the structure of atoms breaks down. The force that keeps electrons in their orbits and prevents them from being crushed is violently overcome. In this crucible of impossible pressure, electrons are slammed into protons, merging to form neutrons and releasing a flood of ghostly particles called neutrinos. The entire core of the star, a region containing more mass than our Sun, is crushed down into a ball of pure neutron degenerate matter only a few kilometers across. This new, incredibly dense object halts the collapse. The infalling outer layers of the star smash against this immovable neutron core and rebound. This rebound creates a shockwave of unimaginable power that tears through the rest of the star, blowing it apart in a supernova explosion. For a few weeks, this single explosion can outshine its entire host galaxy, a final, glorious testament to the death of a giant. Left behind in the silent aftermath is the corpse, a neutron star. A quiet, city-sized sphere holding all the mass of the collapsed core, spinning with incredible speed. Like an ice skater pulling in their arms, the original, massive, slowly rotating star has shrunk, and its rotation has sped up dramatically, sometimes to hundreds of times per second. It no longer generates new heat, but it is born incredibly hot, with temperatures in the trillions of Kelvin, before rapidly cooling to around 1 million Kelvin over a few years. Even an old, cold neutron star can have a surface temperature of over 400,000 Kelvin, compared to our Sun's 5,780 K. This is the object now hanging in space before you. It is not just matter, it is a monument to a cosmic battle between fusion and gravity, a battle that gravity ultimately won. The approach, a warped universe. Your journey toward the neutron star began from what felt like a safe distance. But in the vicinity of a neutron star, safe is a relative and rapidly shrinking idea. Long before you are close enough to touch it, the universe around you begins to warp, and your body is assaulted by forces that have no equivalent on Earth. The first and most overwhelming force is its gravity. The surface gravity of a typical neutron star is about 200 billion times stronger than Earth's. If such an object were to replace our planet, its gravity would be so powerful that light itself would be visibly bent. Standing on its surface, the effect would be so extreme that you could see the back of the star wrapped around the horizon. But you would never make it to the surface. The real danger is not just the strength of the gravity, but the asterisk gradient of that gravity. This is what creates tidal forces, the same forces that cause tides in Earth's oceans, but magnified to a nightmarish degree. As you fall toward the star, the pull on your feet, which are slightly closer, is exponentially stronger than the pull on your head. This differential pull begins to stretch you. At first, it is a subtle, uncomfortable feeling. But the closer you get, the more violent the stretching becomes. The force difference across your body grows from pounds to tons, to thousands of tons, to millions. This process has a quietly terrifying name: spaghettification. Your body is drawn out into a long, thin strand of matter. Your joints would dislocate. Your bones would snap and pulverize. Your skin, muscles, and organs would be ripped apart and stretched into a flowing stream of organic material. This is not a slow process. It happens in an instant, a final, horrifying moment of being unmade by the raw curvature of spacetime. For any object larger than an atom, this is the inevitable fate long before contact. But let's imagine you could somehow survive the tidal forces. The environment you are plunging into is still a storm of lethal energy. Neutron stars have some of the most powerful magnetic fields in the known universe, trillions of times stronger than Earth's. A special class, known as magnetars, have fields 1,000 times stronger still. These fields are so powerful they can distort the shape of atoms themselves, stretching them into thin cylinders. As you approach, you are flying into a blizzard of high-energy particles. You would be bombarded with a lethal dose of X-rays and gamma rays from millions of miles away. This radiation would cook you from the inside out, destroying your cellular structure. A starquake on the crust of a magnetar can release more energy in 1/10 of a second than our Sun has in the last 100,000 years. A blast that would be lethal from light years away. And then there is the heat. Even an old neutron star has a surface temperature of around 1,000,000 Kelvin. The thermal radiation alone would be enough to vaporize you into a thin mist. Even time itself is not safe here. According to Einstein's theory of general relativity, intense gravity warps time. For an observer far away, your clock would appear to slow down as you fell deeper into the star's gravitational well. Your final second would be stretched, from their perspective, into a longer demise. For you, however, time would feel normal, even as your body was being subjected to the most extreme conditions the universe has to offer. The universe is trying to kill you in every way imaginable, and it is succeeding. The contact, the final moment. Let us bypass all the horrors of the approach. By some impossible magic, you have survived. Your gloved finger, impossibly, is just an inch from the surface. The surface appears perfectly smooth. Mountains on a neutron star, if they exist, can only be millimeters high before the immense gravity crushes them back down. You are about to touch the densest material in the universe. This is your final second. As your fingertip crosses the final threshold, it does not touch the surface in any way we would understand. The atoms at the tip of your glove are not met with resistance. They are met with annihilation. The gravitational acceleration at the surface is so extreme that any matter falling onto it reaches a significant fraction of the speed of light. An object dropped from just 1 meter above the surface would impact at over 1,000,000 kilometers per second. So, as the first atoms of your body arrive, they slam into the ultra-dense surface with incomprehensible energy. Each atom does not bounce or crush. It detonates. The impact triggers a cataclysmic burst of gamma rays and X-rays. Your entire body mass, hitting the surface at near relativistic speeds, would release energy that would dwarf the entire nuclear arsenal of our planet. But even this description fails to capture the intimacy of the destruction. Let's zoom in on a single atom in your fingertip. As it approaches the surface, the tidal forces, which we saw act on your whole body, now act on the atom itself. The electron cloud is ripped away from the nucleus. The nucleus itself is torn apart. Your body is not vaporized. It is disassembled. It is unmade, piece by piece, at a subatomic level. The very concept of you ceases to exist before your nerves can fire a signal to your brain to register contact. There is no pain. There is no thought. There is only a conversion of mass into a spectacular, final, and utterly complete blast of pure energy. What's left of you, now a stream of fundamental particles, does not rest on the surface. It is immediately and violently assimilated. The pressure is so great that any remaining protons and electrons are instantly crushed together to form more neutrons. Your matter becomes part of the neutron star. You are not on it, you are in it. Your atoms are now just another layer of neutron degenerate matter, indistinguishable from the rest of the star. Your final act in the universe was not to touch a star, but to become a brief, violent, and ultimately insignificant part of it. A journey inside the layers of a star. The cataclysm of your arrival is over. Your particles now lie on, or rather in, the surface of this cosmic object. But what is this substance you have become a part of? What lies beneath the impossibly smooth crust? To understand a neutron star is to take a journey through states of matter so bizarre they sound like science fiction. Let's descend. The outermost layer, the atmosphere, is thought to be a plasma of hydrogen and other elements, only a few centimeters thick, held in place by the colossal gravity. Immediately below this lies the outer crust, a few hundred meters deep. Here, the pressure is already immense. Matter is composed of atomic nuclei, likely iron, crushed into a solid crystalline lattice. A sea of electrons flows freely through this rigid structure. As we descend further, we cross a threshold into a realm of physics that earns the whimsical, yet unsettling, name, nuclear pasta. Here, the pressure becomes so overwhelming that even the tightly packed atomic nuclei can no longer maintain their spherical shape. The competing forces, gravity crushing everything, the nuclear force binding particles, and electrostatic repulsion pushing them apart, enter a bizarre state of equilibrium. This conflict forces the nuclear matter to arrange itself into complex geometric patterns. Physicists named these structures after pasta. Near the top of this layer, the nuclei are squeezed into bubble-like shapes, a phase known as gnocchi. As we go deeper, these clumps are fused and elongated into long rods, the spaghetti phase. Deeper still, the pressure squashes these rods into wide, flat sheets, forming the lasagna phase. These pasta shapes are not just a quirky analogy. Computer simulations suggest that nuclear pasta is the strongest material in the entire universe, perhaps 10 billion times stronger than steel. This single layer, though only about 100 meters thick, is so dense it contains more mass than thousands of Earths. As we continue our descent, the roles of matter and void reverse. We find long cylindrical holes, bucatini, or anti-spaghetti, and even a Swiss cheese phase with spherical voids. Finally, as we reach the bottom of the inner crust, the pressure becomes too great even for these exotic pasta structures. The last vestiges of individual nuclei dissolve, and we transition into the star's core. You have now traveled through a 100-meter-thick layer of the universe's most bizarre and strongest material, a journey through a subterranean, subatomic kitchen cooked up by gravity itself. The unknowable core, a superfluid mystery. We have arrived at the heart of the neutron star. This is a region of ultimate mystery, a place where our current understanding of physics is pushed to its limit. The density and pressure here are so extreme they cannot be replicated on Earth. What happens to matter under these conditions is a subject of intense theoretical debate. The most conservative model describes the outer core as a sea of neutron degenerate matter. But it is not a simple liquid. At these densities, the neutrons are expected to form a superfluid, a quantum state of matter with zero viscosity, meaning it can flow without any friction. A vortex in a neutron star's superfluid core could, in theory, spin forever. Mixed within this neutron superfluid is a smaller population of protons. These protons are predicted to become a superconductor, allowing electricity to flow with zero resistance. The immense electrical currents flowing in the proton superconductor are believed to be the source of the neutron star's colossal magnetic field. The core is a bizarre quantum cocktail, a frictionless superfluid of neutrons interpenetrating a perfect superconductor of protons. But this is just the beginning of the mystery. As we plunge toward the center, the pressure continues to rise to a point where even neutrons themselves might not be stable. What lies in the absolute center is one of the biggest unsolved questions in modern astrophysics. One theory proposes that the pressure becomes so great that neutrons break down into their constituent particles, quarks. This would create quark matter. In the normal universe, quarks are always confined in groups. But in the core of a neutron star, they could become deconfined, roaming freely in a dense soup. If this is true, neutron star cores are the only places in the modern universe where this primordial state of matter, which existed only in the first microseconds after the Big Bang, can exist stably. Some theories go even further, suggesting the core contains strange matter, a hypothetical form of quark matter that includes strange quarks. In some models, strange matter could be the most stable form of matter in the universe. Other exotic possibilities exist. The truth is, we do not know. The core of a neutron star is a locked box. Scientists use the data we can gather, a star's mass, its radius, its spin rate, to rule out different models. Every observation adds another clue, helping us to slowly unlock the secrets hidden within these incredible objects. The center of a neutron star remains one of the last and greatest frontiers of physics. The fragility of everything, a reflection. Our journey to the surface of a neutron star has been a tour of physical extremes. But the story of the neutron star is more than a collection of facts. It is a profound meditation on the nature of matter, and on the delicate set of rules that allow for our own existence. Everything you consider solid is a ghost. The atoms that make up your body, the chair you're sitting on, the ground beneath your feet. They're over 99.9% empty space. The feeling of solidity is an illusion, a trick of the electromagnetic force. When you press your hand against a wall, you are not touching it. The electron clouds of the atoms in your hand are repelling the electron clouds of the atoms in the wall. This repulsive force is the only thing preventing your hand from passing right through it. Our world is built on this principle of repulsion. We exist in the comfortable emptiness between atomic nuclei. A neutron star is what happens when this fundamental principle fails. It is a place where gravity has become so powerful that it has broken the illusion of solidity. It has crushed the empty space out of existence. It has defeated the force that holds up everything from white dwarf stars to the mountains on Earth. In its place, a new force, neutron degeneracy pressure, arises to halt the final collapse into a black hole. A neutron star exists on a knife's edge. Add just a little too much mass, and even this final defense will fail. The star will cross what is known as the Tolman-Oppenheimer-Volkoff limit, a mass of roughly 2.2 times that of our Sun. Beyond that point, nothing can stop the collapse. It will become a black hole, and its surface, its core, and all the bizarre physics within will disappear forever behind an event horizon. Looking at a neutron star forces us to confront the fragility of our own reality. The forces that make our world seem stable are, on a cosmic scale, remarkably weak. We live in a low-gravity, low-energy corner of the universe, and it is only in this sheltered environment that the complex structures of life can form. The universe is not obligated to be comprehensible or hospitable. The nuclear pasta, the superfluid core, the potential quark soup. These are reminders that our understanding is incomplete, and that nature's capacity for creating extreme phenomena is likely far greater than we can imagine. To touch a neutron star is to touch the physical limit of matter. It is to be annihilated by the same forces that forged the heavy elements in the cosmos. In a very real sense, the violence of a neutron star is woven into the fabric of our world. So while the act of touching one would be your last, the journey teaches us a final, profound lesson. It reveals that the boundary between existence and annihilation is simply a matter of pressure. And that the stable, solid world we inhabit is not the default state of the universe, but a beautiful, fragile, and incredibly lucky exception. If this kind of calm exploration into the world of physics helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether near an ocean, a forest, a city, or somewhere quiet in between, feel free to share where you're watching or listening from. Let us know in the comments which cosmic extreme you'd like to visit next. From its violent birth in a supernova to its enigmatic, unknowable core, the neutron star stands as a testament to the power of gravity. It is an object that is simultaneously simple, a city-sized sphere of neutrons, and impossibly complex, containing states of matter that challenge the foundations of physics. Our journey to its surface was a hypothetical one, ending in instant annihilation, but it reveals a fundamental truth about our universe. The laws of physics can produce objects of both breathtaking beauty and terrifying violence. A single teaspoon of its substance weighs more than a mountain, a fact that is as humbling as it is mind-boggling. It is a celestial ghost, a cosmic relic, and a natural laboratory for the most extreme physics imaginable. By studying these objects from afar, we learn not only about the life and death of stars, but about the fundamental nature of the matter and energy that constitute everything. Your final second touching a neutron star is a story of ultimate destruction, but it is also a story of ultimate discovery, a glimpse into the raw, untamed heart of the cosmos.